For weeks, Mars has been whispering, and then, one night, it went completely still. The orbiters that once pulsed with data fell into a synchronized quiet, as if every machine orbiting the red planet had agreed to hold its breath. No transmissions, no press briefings. Just a low humming void between worlds. It's November 26th, 2025. Somewhere in that silence, the interstellar traveler, known as 3I divided by Atlas, slides past Mars, 30 million kilometers away, moving through the thin geometry of sunlight and dust. For months, agencies across Earth had prepared for this encounter, scripting the press releases before the data even arrived. But the data never came. Instead, what reached us was an echo, a pattern too faint to classify, too stubborn to ignore. A stack of unverified images began to circulate in private channels, frames from an unknown analyst stitched together in the middle of the night. There, above Mars's horizon, a bluish shimmer drifted where no reflection should exist. It wasn't proof. It wasn't an artifact. It was something in between, a pulse of light that carried more questions than photons. People started watching the silence itself, because when data stops flowing, it means leaks. Was it a malfunction, a cosmic coincidence, or the quiet brush of something not built by human hands? Every silence tells a story, and this one feels intentional, because sometimes, before revelation, the universe pauses just long enough for us to realize it's been watching back. It started with a single frame, an image that shouldn't exist, and yet it did. In the calm, after weeks of silence from Mars, a faint blue smudge appeared on a stack of images quietly traded among a small circle of data analysts. No headline, no leak announcement, just a compressed TIFF file with a cryptic tag, MZ stack 112,625 V3. No one knew where it came from. Everyone wanted to believe it was real. The frame showed a slice of Martian sky faintly illuminated, almost electric in its quiet blue. It wasn't a beam or a streak, more like a breath frozen in pixels, thin, deliberate, and impossibly precise. To anyone outside the community, it looked meaningless. To those who knew what was happening around 3I divided by Atlas, it was an alarm bell. If the metadata were genuine, the image had been captured by Mastcam Z, a stereo camera aboard Perseverance never designed for astrophotography. Its purpose was to study rock textures, not stars. Yet here it was, aimed at the night sky, exactly when the interstellar object passed near Mars on November 26, 2025. No official mission logs mentioned such a command. No public API recorded any upward-pointing sequences. And still, the picture existed. People began dissecting it like forensics experts at a digital crime scene. Was it a deliberate test image? A software glitch? Or the first off-world detection of an interstellar traveler? The discussion exploded within hours. Astrophotographers noted the absence of cosmic ray hits, tiny white specks that always litter long exposures. Some argued that alone proved it was synthetic. Others countered that modern noise filters could remove those traces automatically. One engineer ran a noise analysis, showing that the blue channel carried a perfect Gaussian curve, while red and green showed the usual thermal spikes. That asymmetry was unsettling. Real data is messy, imperfect. This one looked curated. Forums lit up with side-by-side comparisons. People pulled calibration frames, overlaid them with the leaked stack, and measured subpixel drift. Someone noticed that the star field matched predictions for that night, but the anomaly didn't align with any known star, asteroid, or instrument reflection. The geometry was precise, but its color was wrong. Mastcam Z filters shouldn't even register that wavelength without extreme overexposure. By dawn on November 28th, the story had leaked beyond the technical forums. Tweets, podcasts, and even fringe news outlets picked it up, calling it the image NASA forgot to mention. We flack the signed, the slav, and a braid, and find. Within 24 hours, it became the most downloaded scientific file on encrypted servers across 3 continents. Not because it proved anything, but because it didn't. Its ambiguity was addictive. And somewhere between curiosity and disbelief, something cracked open. For the first time in months, the silence around 3I divided by Atlas had broken not through words, but through a blur of pixels. The universe had whispered again, and no one could agree on what it said. Inside observatories, professionals stayed quiet. They knew that if the frame was genuine, it violated multiple data handling protocols. Each image from Mars passes through calibration pipelines, checksum validation, and metadata encryption before release. If a file escaped early, it meant someone on the inside had either made a mistake or made a choice. But beyond speculation, one fact remained. The object was exactly where 3i divided by Atlas should have been. Its motion, inferred from 3 stacked frames, hinted at parallax consistent with a moving source near 0.2 AU beyond Mars. No cosmic ray hit, no star bleed, no dead pixel clusters. Just that blue smudge, unshakable, defiant, alive. By the end of the week, an undercurrent had formed. Some whispered that the leak was a controlled release meant to test public reaction. Others said it was a rogue scientist trying to warn us before data suppression began. Most just stared at the image, replaying it frame by frame, searching for a flaw that would make them feel safe again. Because if the leak was real, it wasn't just a picture. It was a question. And questions can be far more dangerous than answers. The following week became a blur of code, sleepless nights, and half-broken servers. Every digital astronomer on Earth was trying to rebuild the leak. It wasn't curiosity anymore, it was obsession. They scraped every frame from Perseverance's public archive, matching timestamps from Sol 1743 to 1746. The idea was simple. If the leak was real, it could be reproduced. If it couldn't, then the truth itself had been tampered with. But reproducibility is cruel. It requires order, metadata, context, and those things were missing. Every stack needs alignment data. How the frames overlap, how the bias subtraction was applied, and which channel matrices were weighted. Without that, it's like assembling a mirror from broken shards. You can guess the reflection, but never trust it. One research collective in Lisbon claimed success. Their reconstruction showed a similar glow, but tilted by 3 arcseconds. They said the shift proved it was an optical ghost, sunlight bouncing between the upper lens and a reflective dust grain. Another team in California disagreed, publishing a simulation showing that such a ghost would have been green, not blue. The debate became personal. It wasn't about data anymore. It was about pride. Then a third theory emerged, something quieter, almost plausible. A color scientist from Tokyo proposed that the anomaly came from a channel misregistration between the red and blue bands. If the stacking algorithm interpolated slightly out of phase, residual compression noise could masquerade as a signal. He even wrote a model showing how subpixel drift could produce the exact hue curve seen in the leak. It fit perfectly until someone pointed out the signal persisted across all 3 color layers. Artifacts don't survive that way. Every explanation collapsed under its own precision. Each answer solved part of the puzzle, never the whole. And through it all, the blue smudge refused to vanish. By December 1st, the discussion had evolved into something more philosophical. A veteran astrophysicist asked in a live stream, "What happens when an anomaly is more reproducible socially than scientifically?" His point was brutal. The leak had achieved cultural reproducibility. It spread faster than verification could catch it. It had become an idea, immune to calibration. Meanwhile, NASA's public logs confirmed that Mars-Cam-Z had indeed recorded a set of unusual skyward exposures that week. But the official statement offered no images, only a note that the sequences were under internal review for non-standard telemetry. To the community, that line read like code for, "We saw something, but we don't know what it is." A handful of journalists began tracing digital breadcrumbs, FTP logs, internal mirrors, checksum mismatches. They found a peculiar detail. One missing file ID between the last publicly archived Sol 1746 frame and the first Sol 1747. The absent entry was exactly where the leaked image's timestamp would have fit. That discovery reignited everything. Suddenly, the conversation wasn't about optics or software anymore. It was about integrity. If an image can vanish from an official archive yet appear anonymously online, where does credibility live? In the file header? In the checksum? Or in the collective agreement that something once existed, even if it's been erased? Forums became battlegrounds. On one side, the skeptics armed with equations, alignment charts, and color matrices. On the other hand, the believers armed with conviction and a single JPEG that refused to disappear. Both sides were chasing the same ghost through different wavelengths of faith. By December 3rd, the first mainstream article appeared, "The Smudge That Split Science." It wasn't wrong. The story had stopped being about 3i divided by Atlas itself and had become about us, our relationship with uncertainty, our need for proof that fits our narrative. In the end, the leak might prove nothing. But it revealed something far more fragile: how modern science balances on a thin line between transparency and trust. One analyst summarized it perfectly in a post that went viral. The blue isn't the mystery. The mystery is how much of ourselves we see in the blue. The rest of Bardand, into nice resoir. That sentence stayed pinned to the top of every forum thread for weeks. Because, deep down, no one was arguing about a pixel anomaly. They were arguing about belief, about whether silence still means truth in an age when anyone can fake the sound of revelation. And that, more than the image itself, was the real leak. The night the leak went global, every monitor in every lab glowed the same eerie blue. Screens across time zones flickered with copies of the same frame compressed, re-uploaded, corrupted, restored. No one knew where the first upload came from. Everyone was downloading it. By midnight UTC, the image of the 3i divided by Atlas smudge had become a digital contagion. Cloud drives mirrored it under disguised file names, firewalled institutions scanned inbound packets, and private Slack channels buzzed with spectral overlays. It was the first time in modern astronomy that a mystery spread faster than an official statement. The file wasn't just being studied, it was being hunted. Across Europe, South America, and Japan, independent observatories launched what they called the validation sprint, a global effort to reproduce the leak's spectral fingerprint using publicly available Mars-CAM-Z calibration frames. Each team wanted to be first to confirm or debunk the anomaly. It was a scientific competition dressed as collaboration. At the core of every discussion was one sacred word: reproducibility. In science, it's the firewall between curiosity and chaos. If an effect can't be replicated under known parameters, it's as good as fiction. But the leak didn't care about parameters. Its metadata was missing, its checksum invalid, its origin unverifiable, and yet the pixels were consistent across every copy. Somehow, the corruption had preserved the truth better than the archive. Analysts began dissecting every byte. They measured histogram curves, calculated pixel intensity deviations, and tracked the compression artifacts across re-uploads. What they found was unnerving. Each generation of the file, no matter how recompressed, retained the same spectral asymmetry between 480 and 490 nanometers. That wasn't normal. Compression should smear subtle color peaks. This one refused to fade. Forums exploded. Someone called it data's ghost, a phrase that stuck. Podcasts replayed sound design recreations of what that frequency might sound like if converted to audio waves, a rising hum at 13 kHz, almost biological. YouTube analysts looped it against NASA's archived telemetry to see if any packet signatures matched. They didn't. But the hum remained in people's heads, long after the videos ended. Within 48 hours, the leak had evolved from a JPEG into a phenomenon. Not because it revealed 3i divided by Atlas, but because it revealed something about us. How quickly awe can mutate into obsession. Threads discussing color calibration turned into philosophical arguments about data purity. What does it mean when an unverified image feels more authentic than official data? Meanwhile, on encrypted forums used by data engineers, a different kind of chatter surfaced. Someone claiming to work at a Mars mission subcontractor posted a partial checksum sequence matching the leaked file. If true, it meant the file had once existed inside the official telemetry chain before deletion. But the account disappeared minutes later. No one could verify it. Still, the details spread like plasma through rumor channels. A single checksum confirming existence without context. For many, that was enough. Reproducibility was no longer about recreating the phenomenon, it was about proving that the data ever passed through human hands. In less than 3 days, the world's most brilliant analysts had formed a mosaic of partial truths. A checksum here, a histogram there, a spectral bump frozen in re-encoded noise. None of it explained the origin. All of it made the mystery deeper. And as more labs joined the chase, one unsettling thought began to creep in. What if the reason no one could reproduce the image was it because it was never meant to exist more than once? By December 2nd, the validation sprint had become a battlefield of algorithms. Teams raced to rebuild the stack using open-source pipelines and machine learning alignment scripts. Slack channels overflowed with code fragments, snippets of Python and MATLAB posted faster than anyone could read them. People weren't just running analysis, they were rewriting the definition of replication. To simulate the leak, analysts needed the same sequence of frames, exposure times, and alignment vectors that produced the anomaly. But the original metadata had been stripped. That forced everyone to guess. And guessing in science is both a sin and a thrill. One group at the Independent Validation Network claimed partial success. They ran 247 different stacking permutations using Mars-CAM-Z's publicly available dark frames. On iteration 173, a faint structure appeared, a diagonal streak glowing faintly at 485 nanometers. The lab erupted. For 10 minutes, they thought they'd solved it. Then, when the alignment matrix was rerun with corrected rotation parameters, the streak vanished. The triumph collapsed into silence. The deeper they dug, the stranger the math became. Each time someone adjusted the weighting of the blue channel, the anomaly shifted just enough to remain visible but never stable. It was like chasing a reflection through moving water. One wrong assumption, one misplaced coefficient, and the signal dissolved back into noise. A senior engineer tried a brute force method feeding every plausible exposure set through a neural destriping filter trained on known Mars imagery. The model failed spectacularly. Instead of removing noise, it intensified it, generating phantom halos that multiplied with each pass. For a brief moment, the screens glowed with dozens of artificial smudges, each mimicking the original but none identical. It looked beautiful and horrifying, like an AI dreaming in false color. The breakthrough everyone expected never came, but something subtler emerged. When researchers compared all the failed reconstructions, they noticed a pattern in the errors themselves. Every synthetic stack contained a residual offset, 0.47 pixels, toward the lower right corner. That consistent bias hinted that the leak source might not have been Mars-CAM-Z at all, but a secondary compression tool used during downlink packaging. If that were true, the anomaly wasn't celestial. It was procedural. Still, no one could confirm it. NASA's internal tools weren't public, and without access, simulation remained half-blind. So, the forums turned into tribunals. Each hypothesis was uploaded, dissected, torn apart, and remixed into new versions of the same question. Was the blue smudge the universe speaking, or was it our software mishearing it? Tension built between teams. Some accused others of chasing fame, fabricating confirmations for attention. Others countered that suppressing anomalies was a worse sin than exaggerating them. Academic journals refused to touch the subject, citing non-verifiable source material, but the absence of peer review only fed the fever. By now, the collective tone had shifted. The excitement that once fueled collaboration began to curdle into suspicion. Every dataset looked contaminated, every screenshot potentially doctored. Even checksum chains, once the sacred proof of data integrity, became suspect when people realized how easily they could be regenerated. One post summarized the mood perfectly. We're no longer testing the image, we're testing each other's honesty. The line hit hard because it was true. Verification had turned personal. Friendships fractured over calibration parameters. Mentors blocked former students over alignment debates. What began as a scientific exercise had become psychological warfare conducted through spreadsheets. Late that evening, the Independent Validation Network issued a formal statement. The signal remains unresolved. No reproducible confirmation has been achieved. To outsiders, it sounded like failure. Inside the community, it felt like defeat. Because in science, unresolved doesn't mean uncertain, it means haunted. As the announcement spread, labs went dark one by one. Screens dimmed, message threads slowed, and the excitement that once pulsed through the network dissipated into exhaustion. No proof, no closure. Just that same persistent question glowing at the edge of every failed reconstruction. Why does the impossible always look so real when you're the one measuring it? The week after the validation sprint collapsed, something quieter began to unfold. Researchers stopped arguing publicly, yet the leak refused to die. It lived on in small private exchanges, emails between trusted colleagues, encrypted folders labeled with innocuous names, screenshots traded like contraband relics of a digital age. No one wanted to talk about it anymore, but no one could stop looking. By December 5th, every attempt to rebuild the stack had failed. Somewhere in the math, the ghost of the anomaly persisted, too coherent to dismiss, too inconsistent to prove. It became a mirror, reflecting the limits of human certainty. Every experiment started to feel like an act of faith disguised as computation. In one late-night forum thread, a data scientist from Prague posted a question that silenced the feed for hours. What if reproducibility isn't the test of truth anymore, but its illusion? He argued that modern pipelines were so layered with machine inference and post-processing heuristics that two identical results might still diverge at the subpixel level. The statement hit like a confession. Everyone knew he was right. Science had automated itself past the point of complete transparency. That realization triggered a wave of existential unease. If reproducibility could no longer guarantee truth, then what could? Checksum verification? Metadata lineage? Human consensus? Every safeguard depended on trust, and trust was already fractured. The blue smudge wasn't the problem anymore. It was the proof that the system's confidence mechanism had failed. Some compared it to a theological crisis. In the same way faith once explained what reason couldn't, data had become the new scripture numbers instead of verses, calibration curves instead of miracles. And now, that scripture had glitched. The believers of precision were staring at an unquantifiable thing. By December 7th, the chatter around the leak had faded into what one analyst called a digital afterlife. The image still existed, mirrored endlessly, re-encoded 1,000 times, but the conversation had moved inward. People stopped asking what it was and started asking what it meant. The lines between observation, interpretation, and imagination blurred until they became indistinguishable. A few attempts at closure appeared. One blog post declared the smudge a data hallucination, a byproduct of compression drift. Another paper argued for a possible Martian aurora, triggered by charged dust interacting with 3I divided by Atlas's passing plasma tail. Both theories had math. Neither had conviction. Truth had splintered into elegant guesses. Meanwhile, a quiet irony took shape. The more people doubted the leak, the more powerful it became. Every failed replication only added to its mythology. The blue persisted not because it was real, but because it refused to conform. In a world built on precision, defiance itself became evidence. The last major discussion thread ended with a line that no one argued with. We've built instruments that can read the whispers of distant stars, but we still can't tell when a lie becomes data. It was cynical, maybe even poetic, but it captured the collective exhaustion perfectly. No one knew if the smudge had ever existed in the raw frames. It didn't matter anymore. Its meaning had escaped the data. In the end, the anatomy of the leak wasn't about pixels, algorithms, or verification chains. It was about faith, the faith that human tools can still separate noise from message. And maybe that's the quiet tragedy of the whole thing. In trying to prove what we saw, we forgot how to see. The screen now shows nothing but static. And somewhere beyond Mars, 3I divided by Atlas continues its silent arc through space, carrying with it, perhaps, the only version of the image that was ever real. Silence became protocol long before anyone called it that. Inside every space agency, there's a quiet clause hidden between words like mission integrity and data calibration. It says, when in doubt, hold. When an anomaly appears, you don't announce it, you isolate it. You file it under pending verification and let the calendar do the explaining. By December 8th, 2025, that clause had become gospel. 9 days had passed since the first public replication attempts of the 3I divided by Atlas anomaly. Hundreds of labs had failed to reproduce the blue smudge. Thousands of viewers had demanded answers, and the institutions designed to speak said nothing. The official downlink logs still looked busy. Telemetry packets kept arriving from Mars orbiters, rovers, and relay satellites. But buried inside that flood of numbers was a subtle gap, a blackout window just wide enough to swallow the frames everyone was waiting for. Those missing files never showed up in the public mirror, and no one inside the agencies was authorized to say why. In theory, the process is simple. Every Mars instrument runs a downlink queue. Raw images are compressed, time-stamped, and sent through a deep space relay to Earth. From there, they're sorted by a calibration pipeline, corrected for bias, noise, and geometric distortion before public release. But when a frame triggers internal flags, unusual pixel drift, unregistered sensor angles, or unverified light profiles, it's automatically quarantined. The system labels it non-standard telemetry. It's supposed to be a technical safeguard. In practice, it's the perfect hiding place. The review chain moves slowly. Each flagged image must pass through multiple teams, one for sensor calibration, one for mission priorities, and one for external data policy. That process can take days, even weeks. But when the anomaly in question is being dissected publicly, every minute of silence feels intentional. It doesn't matter if the reason is bureaucracy or caution, the optics look identical. By December 10th, reporters began sending formal requests for comment. The replies were polite, automated, and meaningless. Data review ongoing. No public release date at this time. The wording was almost algorithmic, devoid of tone or urgency. But to anyone who'd been watching the 3i divided by Atlas timeline unfold, it read like a cover story. The public's patience cracked first. Independent analysts, already exhausted from weeks of chasing corrupted checksum trails, began turning their attention toward institutional behavior instead of data. If science couldn't reproduce the truth, maybe silence could. On forums, someone mapped every timestamp from MarsCamZ downlinks against the public archive. They found a pattern: small, repeating lags in the data feed, always near midnight UTC, always aligned with the window when the leak supposedly originated. The delay wasn't random, it was procedural. Inside the agencies, that pattern had a name: priority queue reallocation. When a mission faces bandwidth limits, files tagged as non-critical get postponed in favor of surface science or engineering telemetry. It's efficient, logical, even necessary. But for those outside the system, it looked like censorship disguised as scheduling. Silence, by design, is hard to differentiate from control, and by mid-December, that distinction had vanished completely. Every missing frame felt like a statement. Every day without comment felt like confirmation. By December 11th, the silence had started to echo. Every missing update, every delayed press release was amplified through a restless public desperate for resolution. When institutions refuse to speak, interpretation fills the vacuum. And in that void, frustration metastasized into doubt. The first editorial appeared on a small science blog titled "Why Mars Went Quiet." The writer wasn't accusing anyone, just outlining the strange rhythm of uploads, the irregular calibration logs, the repeated use of the phrase "under review." Within hours, the post was everywhere. Mainstream outlets picked it up, adding their own layers of speculation. Anchors began using the word "withheld." A word like that changes everything. Inside the agencies, comms teams scrambled. They drafted clarifying statements that said nothing, assurances of transparency, reminders that data validation takes time. But time was exactly what the public no longer trusted. 10 days of procedural delay felt like 10 months of manipulation. People wanted footage, not footnotes. A journalist in New York filed a Freedom of Information request for the MarsCamZ telemetry queue. The request was denied within minutes. Mission priority, confidentiality. That phrase hit like a slap. Confidentiality had replaced communication. On social media, timelines are fractured. Some users argued the agencies were victims of their own bureaucracy, that slow science was still science. Others saw a pattern of deliberate containment, a strategy to cool public curiosity until attention faded. One viral post summed it up. "They're not ignoring us. They're waiting for us to forget." The line trended for 2 days straight. Meanwhile, the internal logs told a quieter story. Bandwidth reallocation was legitimate. The engineering data for an upcoming Martian dust storm had priority. But from the outside, that nuance was invisible. All the public saw were timestamps skipping like a heartbeat, each gap feeding another round of suspicion. The tension reached a new pitch when a mid-level analyst leaked an internal memo from December 9th. It contained a single line highlighted in red: "Suspend night sky imaging until public discourse stabilizes." That sentence became the headline heard around the world. To the agencies, it was risk management. To everyone else, it was censorship made policy. Talk shows debated the ethics of silence. Was it better to delay uncertain data or release it and risk misinterpretation? Experts are split down the middle. Philosophers argued that institutional restraint was a form of humility. Journalists countered that restraint without disclosure was deception. The public, watching from behind glowing screens, didn't care about epistemology, they just wanted answers. By December 13th, independent observatories announced a coordinated protest. They would open their raw data archives, no matter how uncalibrated, under a public license. They called it the Open Sky Initiative. The idea spread fast. If the official channels remained quiet, the amateur network would speak instead. Within hours, terabytes of Mars imagery flooded peer-to-peer platforms. Most of it was junk, dust noise, misaligned exposures, but the symbolism mattered. Silence had provoked rebellion. And yet, even rebellion grew weary. As data poured in, none of it revealed the missing frames or confirmed the elusive smudge. The excitement curdled into fatigue. Still, No comment from the agencies. Every passing day turned skepticism into a narrative. The silence had achieved something remarkable. It was now self-sustaining. By mid-December, the phrase institutional blackout became shorthand for the entire crisis. It didn't need clarification anymore. People knew what it meant, not a technical issue, not a bandwidth glitch, but a decision, a choice to say nothing while pretending to be busy. When silence lasts long enough, it stops sounding like protection. It starts sounding like guilt. By December 15th, the silence had turned radioactive. Every attempt to control the narrative only deepened the fracture. When the agencies finally issued a formal statement, it landed like static, a 2-page document full of passive verbs and bureaucratic anesthesia. Phrases like pending calibration and data integrity verification underway replaced any trace of human tone. No one believed it anymore. Reporters tore through every sentence, searching for what wasn't said. There was no mention of 3I divided by Atlas, no acknowledgement of the missing frames, only a vague reference to system anomalies under diagnostic review. It was the kind of language designed to sound safe while saying nothing at all. Even the punctuation felt defensive. The public reaction was swift and merciless. Comment sections overflowed with sarcasm. Memes flooded social media screenshots of empty press rooms captioned, "Mars speaks louder than they do." Late-night hosts joked that silence had become the most expensive sound in space exploration. What began as a data dispute had turned into cultural theatre. Inside the institutions, the mood wasn't defiant, it was exhausted. Engineers whispered about risk assessments, lawyers about liability, administrators about public trust metrics. Someone leaked another memo, this one titled, Information Containment Protocols, December Revision. It stated that any media inquiry referencing the term leak required direct approval from executive offices. To the outside world, it confirmed everything people feared, that silence wasn't a malfunction of bureaucracy, it was policy. For a brief moment, a few insiders tried to push back. An internal letter circulated through encrypted channels, signed by several mid-level researchers. They demanded transparency, arguing that the public had the right to see even uncertain data. The letter ended with a single line, "Science cannot survive behind NDAs." Within hours, the signatories' names vanished from internal directories. No one mentioned them again. Meanwhile, 3I divided by Atlas continued its orbit outward, untouched by the noise it left behind. The irony was unbearable. An interstellar visitor, millions of kilometers away, had managed to expose how fragile Earth's own systems of truth had become. The comet didn't need to do anything, it just had to exist. And humanity did the rest. By December 18th, public attention began to wane. The story was still trending, but fatigue had set in. People moved on to newer controversies, fresher scandals. Silence, once shocking, had become familiar. And that familiarity was the institution's victory. Behind closed doors, the data review continued, slow and methodical. Technicians ran checksum audits, reprocessed telemetry packets, and corrected timestamp mismatches. They were doing their jobs, but no one outside would ever see the results. Every frame recovered went into a restricted directory labeled Provisional Data, Do Not Circulate. The investigation had become its own containment field. In the final briefing of the year, a spokesperson stood before a wall of muted monitors and read from a script. There is currently no verified evidence of unanticipated optical phenomena associated with interplanetary object 3I divided by Atlas. The investigation remains open. It was a sentence polished to death, precise, bloodless, impossible to dispute, and in its perfection, it felt dishonest. After the broadcast ended, a journalist whispered into a live mic still transmitting, "They've learned how to weaponize silence." The phrase spread quietly, too quiet to trend, but it stayed, because it named what everyone already felt. That silence had stopped being an absence of sound and had become a language of power. By the time the year closed, no one expected answers anymore. The files would surface eventually, somewhere, years from now, redacted, renamed, irrelevant. But in that moment, December 2025 belonged to the quiet. It was the kind of silence that doesn't wait for truth. It replaces it. Color should never lie. Yet every telescope said green while Mars whispered blue. By mid-December 2025, the data streams from infrared observatories were unanimous. 3I divided by Atlas was emitting a classic CO2-rich coma signature. Its spectroscopic peaks aligned perfectly with the C two swan bands around 516 nanometers textbook green. Every spectral model, every cometry template, confirmed it. Green was what interstellar comets did when sunlight fractured carbon molecules into excited radicals. It was supposed to be the most predictable color in the cosmos. But the leaked Mars stack refused to cooperate. The anomaly wasn't green at all. It was blue, subtle, soft, impossible. A shade no CO2 coma should produce, at least not under the known grain size distribution models. The blue shimmer didn't fit any of the parameters. Not the dust albedo, not the photometric scattering angle, not the known correlation between nucleus temperature and C2 emission. Physics, it seemed, had contradicted itself. The first responses were defensive. Analysts called it a processing artifact, a color channel bias, a gamma stretch gone wrong. But then the deeper math began to misbehave. When the color ratios were plotted against spectral reflectance curves, the blue anomaly held. Even after correcting for atmospheric scattering from Mars's thin CO2 atmosphere, the hue remained shifted by nearly 20 nanometers toward the cooler end of the spectrum. It wasn't noise. It was a pattern. That was the moment the mood changed from curiosity to discomfort. Color had always been a truth-teller in astronomy. Even across light years, color reveals chemistry, temperature, and motion. To see color break, faith with physics was like watching a compass spin in a magnetic storm. An independent researcher reconstructed the photometry from archived Marscam Z filters, running them through a forward scattering simulation. The result should have shown a predictable green to yellow curve, corresponding to CO2-dominated sublimation. Instead, the curve flattened, showing reflectance peaks around 480 nanometers distinctly blue. The team repeated the test using H2O models, silicate dust, and even nickel vapor lines. Nothing fit. There was no known combination of materials, illumination angle, or grain composition that could shift CO2 emission that far. Some suggested that the answer wasn't physical at all, that the blue was psychological, a perceptual mirage amplified by expectation. The human brain, after all, sees color relatively, not absolutely. But the instruments didn't hallucinate. Spectrometers don't feel. They measure, and they were unanimous. A 480 nanometer spike that shouldn't exist. In the community's chat log, someone wrote, "We've entered the part of the story where color stops being a property and becomes a statement." The line went viral because everyone understood what it meant. This wasn't about pixels anymore. It was about trust. Trust in the instruments, trust in the equations, trust in the idea that nature never contradicts herself. For days, scientists tried to rationalize the inconsistency. They blamed thin-film interference on metallic grains, uncorrected sensor nonlinearity, and even quantum fluorescence caused by cosmic ray bombardment. But the longer the explanations stretched, the weaker they sounded. The blue refused to vanish, clinging to the edge of every recalibrated frame, like a fingerprint left by something that shouldn't have been there. Somewhere between analysis and denial, fascination took hold, because deep down, everyone wanted it to be real. Not because it made sense, but because it didn't. It suggested that something, somewhere, had slipped the leash of expectation, and in science, that kind of disobedience is irresistible. By December 20th, the anomaly had spread beyond curiosity. It had become a contagion of doubt. Color scientists, astrophysicists, and data engineers began forming impromptu working groups, trying to reconcile the impossible hue. They spoke in the language of light, scattering angles, C2 fluorescence, Rayleigh coefficients. Every phrase sounded like reassurance, but behind each was unease. At the Spectral Dynamics Lab in Geneva, a team attempted a full simulation of the 3I divided by Atlas coma. They built a virtual model of the object's dust environment, calculating grain size distribution, refractive indices, and phase functions under Martian solar incidents. The expectation was simple. The simulation would yield green. Instead, it returned a spectrum that drifted toward blue in precisely the same region as the leaked image. At first, they blamed a coding bug. Then they reran the model on a different cluster. The result held. 2 systems, 2 codes, 1 contradiction. Somewhere between data and disbelief, excitement began to pulse again. If the blue was real, it meant something unrecorded was happening in 3I divided by Atlas's coma. Perhaps metallic dust reflecting forward scattered sunlight, or a plasma interaction unknown in typical comet physics. Both options were absurd. Both felt intoxicating. Within 48 hours, half a dozen hypotheses competed for dominance. The forward scattering anomaly, argued that sunlight reflecting off micron-sized grains at near-zero phase angle could shift the visual peak toward blue if the grains were unusually transparent. The metallic vector model proposed that nanometer-thin nickel films, vaporized by solar radiation, were creating interference fringes. Others favored the quantum fluorescence effect a stretch, but one supported by faint energy excesses detected at 486 nanometers. None of these models fully explained the data. Each solved one piece while breaking another. The simulations predicted brightness ratios that didn't match observations. The scattering functions diverged under small perturbations. Every correction produced a new inconsistency. The physics was fraying at the edges. Meanwhile, image analysts dove deeper into the leaked Mars stack. They isolated the blue band, corrected for gamma bias, subtracted atmospheric path length, and reprojected the field into a Lambertian coordinate system. If the hue was an artifact, it should have collapsed under those corrections. It didn't. Instead, the corrected image revealed something worse. The blue was not uniform. It had structure filament-like tendrils, almost vectorized, running tangentially from the coma's core. Real phenomena produce gradients. Artifacts produce patterns. This looked like both. In the forums, someone joked, "Physics is gaslighting us." It was funny only because it felt true. Every dataset confirmed the contradiction. Every solution contradicted itself. The anomaly was now self-sustaining, feeding on verification. Journalists caught wind of the debate. Headlines read, "The comet that changed color." News anchors simplified the nuance. Green equals normal, blue equals mystery. That binary spread faster than any technical report. Suddenly, the world was watching scientists argue about the color of a ghost. Inside the research community, the tension was palpable. No one wanted to be the first to call the blue real, but no one dared call it fake either. A senior photometrist summarized it perfectly during an internal call. "We're trapped between calibration and confession." By the end of that week, something more philosophical crept in. The debate wasn't just about 3I divided by Atlas anymore. It was about epistemology. How many exceptions can truth endure before it stops being stable? If every correction makes the anomaly stronger, are we discovering reality or manufacturing it? The irony was cruel. In trying to bring the color back to green, they had proved that blue was the only thing that wouldn't go away. The final report from Geneva ended with a single line in bold. No known model can simultaneously reproduce the spectral, photometric, and geometric features of the observed emission. In simpler terms, we can't explain it, but we can't unsee it either. By December 22nd, the anomaly had become a kind of mirror the scientific world couldn't look away from. What began as a question of wavelength had turned into a crisis of perception. Every lab still running models felt the same slow dread. Each correction confirmed the contradiction. The more precisely they calibrated, the more defiantly blue the data became. One research team in Chile tried a desperate experiment. They rebuilt the coma model from scratch using an entirely different scattering framework, Henry-Greenstein phase asymmetry, combined with multi-grain Mie distribution. If forward scattering was the culprit, the simulation would push the spectral curve back toward green. Instead, the color deepened. The angle correction amplified the blue component by 12%. The math had started mocking them. In a closed symposium, a senior optical physicist admitted what everyone was afraid to say out loud. Maybe the instruments aren't wrong. Maybe our expectations are. It was a simple sentence, but it felt heretical. Because the foundation of all measurement is faith. Faith that the universe behaves consistently when observed. And yet, here was a data point that refused to conform. Speculation splintered into extremes. One camp claimed 3I divided by Atlas carried compounds never catalogued exotic carbon structures that emitted at shorter wavelengths under intense photolysis. Another group proposed a subtler heresy, that Mars's thin atmosphere, acting as a prism at grazing angles, polarized the coma's reflection in ways no model had ever captured. That theory didn't hold either, but it was beautiful. Science often hides its desperation behind beauty. Public fascination reignited. News outlets framed the debate as a metaphor when the universe disagrees with its own rules. Documentaries showed time-lapse overlays of the comet shifting hues, from emerald to cobalt, accompanied by whispered narration. Even people who didn't understand the physics felt the tension. The color blue had become shorthand for doubt. Inside private forums, the tone was different. Researchers spoke about sleeplessness, burnout, and the quiet humiliation of chasing a ghost that refused to vanish. Some began questioning their calibration tools altogether. What if the problem wasn't the comet or the math, but the sensors themselves? Modern detectors rely on silicon-based quantum efficiency curves tuned to human definitions of color. But those definitions are artifacts of biology, not physics. Maybe, one researcher wrote, we've built instruments that only see what we're comfortable seeing. It was half a joke, half a confession. The Geneva report circulated again, this time annotated. Someone highlighted a passage about grain refractive indices varying with ionization potential. Another added a comment, or maybe something wanted to be seen blue. It was an absurd thought, and yet it stayed in everyone's minds longer than the equations did. As the days passed, a strange calm settled in. No more press releases, no new models, just quiet acceptance that the mystery might never be resolved. But even that acceptance carried unease. If the color was real, it meant the physics of sublimation and scattering weren't universal. If it wasn't, then the collective apparatus of human observation had hallucinated. Either outcome undermined certainty. In the final conference summary of the year, the chair read a statement written by consensus. There exists a measurable deviation in the optical profile of 3I divided by Atlas, inconsistent with current cometary emission theory. No further conclusions can be drawn until new data becomes available. It was cautious, rational, perfectly phrased, and it sounded like surrender. Afterward, the room stayed silent for a long time. Someone projected the Mars image onto the wall, high resolution, color-corrected, stripped of metadata. The blue shimmer glowed faintly against the dust-red backdrop of Mars. No one spoke. A few people simply stared, as if waiting for the color to change back. It didn't. Later, in an after-hours interview, one photometrist summed up what everyone felt. We study light because we think it tells us the truth, but maybe light only tells us what we're ready to believe. And with that, the story of the green that turned blue became something else, entirely a lesson not about comets or spectra, but about perception itself. The color had stopped being a property of matter and had become a reflection of us. In the deep silence of late December, 3I divided by Atlas continued its slow retreat into the dark, carrying its impossible hue with it. A reminder that sometimes, when reality bends, it doesn't break. It simply changes color. Every mystery reaches a point where science stops asking what happened and starts asking what it means. By the last week of December 2025, that was exactly where 3I divided by Atlas stood, balanced between revelation and restraint. After weeks of chaos, speculation, and color wars, the community decided to rebuild its foundations. Not with emotions this time, but with math. The leak had left a scar, a reminder that information without context becomes mythology. So the new goal wasn't to prove or disprove the blue anomaly, it was to quantify its probability. In science, faith returns disguised as statistics. The Independent Verification Network drafted a comparative hypothesis framework, splitting every possible explanation into 3 categories. 1. Natural optical phenomenon, a product of physics yet misunderstood. 2. Instrumental artifact, a malfunction or algorithmic illusion. 3. Artificial signature, a manufactured effect, deliberate or accidental. Each path required evidence, reproducibility, and falsifiability. The first step was to rebuild the spectroscopy chain. Across multiple observatories, multiband photometry campaigns began, tracking 3I divided by Atlas in near-infrared, visible, and ultraviolet bands simultaneously. If the blue hue were real, it should manifest consistently across instruments. If not, the inconsistency would betray an artifact. The data trickled in. Most ground-based arrays recorded spectra that leaned neutral green consistent with a CO2A dominated coma. But 2 orbital platforms, equipped with high-dispersion spectrometers, showed faint residual emission near 485 nanometers, the same region everyone had fought over. The difference was subtle, a whisper of energy barely above noise but statistically significant. It was enough to reopen curiosity without reopening hysteria. Next came the polarization tests. If the anomaly originated from dust reflection, its polarization angle should vary predictably with phase geometry. If the blue was intrinsic to the material, polarization would remain fixed. Weeks of observations revealed a weak but steady polarization vector, tilted 3 degrees from the theoretical scattering plane. It wasn't proof of anything, only a small defiance of expectation. But sometimes, that's where discovery lives. Analysts built checklists like detectives. Is the spectral slope consistent across instruments? Does the anomaly persist after atmospheric correction? Can it be reproduced under controlled exposure stacking? Every question was a rung in the ladder out of chaos. For the first time since the leak began, the tone of the discussion was calm. The storm had burned itself into discipline. Still, a quiet humility filled the reports. One paper noted that the entire investigation hinged on the assumption that our models of scattering are complete. What if they aren't? Mars, with its thin atmosphere and red dust, offers a geometry no lab can mimic. Light behaves differently in alien air. Perhaps the blue wasn't wrong, it was simply untranslatable. In that possibility lay a new kind of hope. Not the desperate hope of proof, but the measured kind that whispers. We may not understand this yet, but it's still ours to explore. It was the first time the community felt peace with uncertainty. Because to accept mystery isn't to surrender to it, it's to make room for the next question. And so, the investigation of 3I, divided by Atlas, moved from panic to patience. The blue had not vanished. It had only changed context from anomaly to opportunity. By the first week of January 2026, the investigation had matured into a quiet ritual of logic. Emotion had burned away, leaving only comparison. Each hypothesis stood side by side like suspects under neutral light. Science, when done honestly, is less about conviction than elimination. The natural optical phenomenon model came first. Its advocates argued that 3I divided by Atlas simply broke the mold of known comets. Perhaps its nucleus was coated in exotic carbonates or silicate composites forged in a stellar nursery, unlike our own. Such materials might scatter light differently, producing a cooler hue under solar excitation. Simulations based on variable refractive indices supported the possibility, but only barely. The models matched the observed spectrum for 6 of 10 parameters. The remaining 4 refused alignment. When the statistical residuals were plotted, they formed a stubborn curve. Small, consistent, unexplainable. It was as if the comet wanted to stay blue. Next came the instrumental artifact hypothesis, the one most engineers preferred. It proposed that the anomaly was an echo of compression noise masquerading as light. Every transmission from Mars to Earth undergoes multiple encodings, downlink packaging, packet segmentation, and adaptive bit correction. Each step introduces rounding errors, subtle quantization drifts, and interchannel phase shifts. Under normal conditions, these are invisible. But if a single calibration constant drifted by even 0.0003, it could tilt color matrices enough to mimic a faint spectral offset. That theory fits neatly. Too neatly. When analysts reconstructed the leak using the proposed offset, the color vanished, but so did several legitimate stars from the background. Artifacts explain themselves perfectly only when they rewrite reality. The third possibility carried a faint tremor of audacity, the artificial signature hypothesis. No one wanted to write those words, but curiosity is stronger than caution. This model didn't claim alien intent. It merely acknowledged that deliberate modulation of reflectance could, in theory, reproduce the spectral anomaly. If an object's surface contained patterned crystalline arrays or thin film structures capable of diffractive reflection, it might generate specific hues independent of composition. We build such materials on Earth: metamaterials, photonic lattices, diffraction gratings. Nature builds them too, but rarely with such precision. If 3I divided by Atlas bore even trace evidence of that geometry, it would rewrite more than comet science. Each hypothesis came with its verification checklist. Spectral continuity. Does the blue peak persist across independent detectors? Geometric invariance. Does the hue remain constant with phase angle shifts? Polarization correlation. Does the reflection vector align with natural scattering models? Spectroscopy consistency. Do spectral lines correspond to known molecular transitions? Every test returned the same ambiguous verdict. Almost yes, almost no. The reports read like legal transcripts, dense, unemotional, haunted by precision. But between the numbers, something quiet glimmered. In the margins of one paper, an anonymous reviewer scribbled a note: "If anomaly survives all models, then anomaly becomes the model." It wasn't cynicism, it was evolution. For the first time since the leak began, the community shared a strange consensus. The question wasn't whether 3I divided by Atlas had defied expectation, but how long science could resist redefining expectation itself. And there, beneath the data tables and uncertainty intervals, a delicate form of hope emerged, Not the naive kind that seeks miracles, but the disciplined kind that accepts the unknown as fertile ground. The word implies regained its weight. The leak didn't prove anything. It suggested. It whispered that perhaps the boundaries of comprehension are elastic, that error and discovery sometimes wear the same wavelength. When the summary conference concluded, one physicist closed her notes and said quietly, "If the universe can color outside its own lines, maybe we should stop erasing." No one argued, because somewhere between green and blue, reason had found something better than certainty. It had found wonder again. By mid-January 2026, the investigation had stopped chasing answers and started tracing implications. What the leak revealed wasn't just a comet's color, it exposed the fragile architecture of certainty itself. For decades, science had relied on a simple covenant: observe, measure, repeat. Now, repetition is no longer guaranteed to provide understanding. Truth had become probabilistic, and that was strangely liberating. The final round of reviews organized every finding into 3 columns: observation, explanation, and consequence. The table looked orderly, almost comforting, but the words inside it carried unease. Under observation, an unverified blue spectral shift near 485 nanometers. Under explanation, unknown. Under consequence, redefinition of observational reliability in low-signal regimes. It read less like a conclusion and more like a confession. A new team proposed a meta-analysis of consistency. Instead of deciding which hypothesis was correct, they compared how each behaved under stress. They discovered something remarkable. The more a model depended on human assumptions, color calibration, expected emission curves, normalized baselines, the faster it broke. The less expectation it carried, the longer it survived. In that discovery lay an uncomfortable truth. Bias wasn't a flaw of individuals. It was the gravitational field of comprehension itself. Meanwhile, 3i divided by Atlas continued outward, its brightness fading by the day. It no longer mattered whether the blue existed in the comet or in our instruments. What mattered was that we had seen it. The event had expanded science's vocabulary, adding one more shade to the spectrum of doubt. During the closing colloquium, a veteran astronomer summarized the collective mood. The leak reminded us that the universe still surprises us because we've become very good at preventing surprise. The room stayed quiet, not from discomfort, but from recognition. Every person present had spent a career turning chaos into curves, mystery into metrics. Now they were remembering why they'd started looking up in the first place. The discussion turned to practical reform. New calibration protocols required dual sensor verification, mandatory open-access raw data release after 72 hours, machine learning correction filters redesigned to flag improbable, not discard them. Policy papers rarely inspire emotion, but this one did. Each paragraph felt like restitution, a promise to listen better next time. When the final report was released, it avoided sensational language. No mention of anomalies or suppression, no grand claims. Just one quiet sentence at the end. Further observation recommended. Apparent inconsistencies may represent unmodeled scattering behavior. But between those careful words, readers sensed something new. Not certainty, but equilibrium. Outside the conference hall, snow drifted under pale January light. One researcher lingered by a window, watching the brightness scatter through ice crystals. Every flake reflected faint bands of green and blue, overlapping so perfectly that color ceased to be distinct. She smiled, realizing that perhaps the answer had been visible all along. Nature never chooses between shades. It holds them both until perception catches up. In the following weeks, public interest waned. The story slipped quietly from headlines, replaced by newer mysteries. Yet within laboratories, the phrase, "the green that turned blue," became shorthand for epistemic humility, a reminder that even in precision, awe has a place. No data was wasted. Every failed reconstruction became part of a larger calibration of thought. That was the true implication of the leak. It didn't change science's direction, it deepened its patience. Somewhere beyond the orbit of Mars, 3i divided by Atlas rotated slowly through sunlight. Its spectrum blended with the cosmic background until both were indistinguishable. For the instruments still tracking it, the numbers flattened, the signal dimmed, and silence resumed. But this time, silence didn't feel empty. It felt earned, like the pause after comprehension, when mystery and understanding finally share the same light. The universe hides its mistakes in degrees, not distances. That was the quiet lesson that began to surface in February 2026, when the investigation into 3I divided by Atlas took an unexpected turn, not through discovery, but through geometry. After months of spectral debate and color wars, the team decided to re-examine something deceptively simple: the phase angle, the apparent angle between the Sun, the comet, and the observer. Most early analyses had assumed a fixed geometry, near zero phase, meaning sunlight reflected almost directly back toward the instruments. But someone noticed a small discrepancy buried in a calibration log: 5.07 degrees plus or minus 0.12, a number so small it seemed irrelevant until it wasn't. That 5-degree offset changed everything. At low phase angles, scattering behaves predictably: light bounces straight, intensifying brightness and flattening color. But shift the geometry slightly, and forward scattering takes control. Photons begin grazing dust grains instead of striking them head-on. The coma's reflective behavior warps, emphasizing wavelengths that depend on grain size, density, and orientation. In short, 5 degrees can make green look blue. This wasn't new physics. It was forgotten nuance. A misaligned assumption masquerading as an anomaly. And yet, it took 3 months, hundreds of simulations, and a global controversy before anyone looked closely enough to see it. The discovery didn't arrive with fanfare. It came buried in a methodology note posted by a graduate student from Kyoto. Phase correction parameters appear misapplied for Mars relative geometry. No one noticed at first. Then a senior spectroscopist read the post and froze. The entire dataset, every replication, every color reconstruction, had treated Mars's local scattering environment as isotropic. It wasn't. Mars adds its own angle to everything. Once recalculated, the results snapped into alignment. Spectral curves rebalanced, polarization shifted back toward predicted values, and the blue signature weakened. Not gone, but diminished. The comet hadn't lied, the math had drifted. Still, the revelation didn't feel triumphant. If anything, it humbled everyone involved. The mystery wasn't solved, it was reframed. Even a perfect measurement can fail if taken from the wrong angle. At the next roundtable meeting, one researcher sighed and said, "We spent 2 months debating the meaning of blue, and it was just geometry reminding us who's in charge." Laughter rippled, thin but genuine. They weren't laughing at the mistake, they were laughing at the scale of their certainty. A new phrase began circulating through the community: "Check your 5 degrees." The few is not beegery. It became shorthand for methodological vigilance, the idea that before chasing the extraordinary, one should measure the ordinary again, but better. Teams started cross-validating every observation with parallel instruments, enforcing dual-angle verification for future missions. It wasn't bureaucracy. It was humility, encoded into protocol. Ironically, that same 5-degree offset sparked a different kind of fascination. If such a small angular shift could reshape light so dramatically, what other phenomena might hinge on equally invisible parameters? Perhaps anomalies weren't signs of cosmic secrets, but reminders of human limits. Reminders that truth depends on where you stand. By the time the revised data circulated, the tone of the conversation had changed completely. No more speculation, no conspiracies, no viral threads, just an almost sacred respect for precision. And beneath that precision, a quiet warning: the difference between discovery and delusion is sometimes less than 5 degrees. By the second week of February 2026, the tone of the investigation had shifted from defense to discipline. Every observatory on the rotation schedule began running high-cadence photometric sweeps, sampling the light curve of 3I divided by Atlas every 30 minutes instead of once per orbit. The goal wasn't to capture drama, it was to measure patience. The 5-degree revelation had changed the field's vocabulary. Scientists were no longer chasing anomalies, they were calibrating humility. To quantify the correction, teams reconstructed the comet's reflectance geometry from scratch. They used new software that incorporated both planetary parallax and phase angle drift over time, accounting for how Mars's orbital tilt subtly refracted sunlight before it reached the comet's coma. This time, the math behaved. The blue curve began to relax back toward green, its amplitude shrinking logarithmically as cadence density improved. Every added data point acted like a confession, pulling color and confidence closer together. Yet no one declared victory. Instead, the findings triggered a collective unease. If such a small oversight could distort truth so convincingly, what else in the archive might hinge on similar ghosts of geometry? Auditors began re-examining unrelated datasets, Venus cloud polarimetry, asteroid albedo catalogs, even archived spectral profiles from deep space probes. They found other 5-degree ghosts everywhere, small, cumulative misalignments that never made headlines but might have nudged entire theories one fraction closer to fiction. It was sobering. The problem wasn't deception, it was scale. Science had grown so vast that its errors had learned to hide between decimals. What the 3I divided by Atlas case exposed wasn't incompetence, but entropy. The slow drift between observation and interpretation. In an internal report circulated among the spectral alignment teams, a single paragraph stood out. Precision without redundancy is performance art. It meant that no matter how perfect one measurement seemed, it wasn't the truth until another instrument agreed. Cross-validation became the new ritual. Labs paired instruments at different longitudes, ensuring simultaneous capture of the same event from multiple angles. If the geometry could betray them once, they would surround it next time. The reforms spread quickly. Data pipelines were rewritten to include angle-based metadata, tagging a simple addition that documented each frame's relative position to both the Sun and the planetary horizon. Future archives would carry this information by default, eliminating ambiguity at the source. A few administrators resisted at first, citing bandwidth costs, but the cultural momentum was unstoppable. The cost of confusion was now higher than the cost of caution. Meanwhile, the public barely noticed. The storm had passed. The comet had faded from headlines. But inside the quiet hum of observatories, something profound was happening. Science had rediscovered its capacity for awe, not in anomalies, but in the discipline of correction. Every recalculated angle felt like an act of reverence. During a midnight observation session, a spectroscopist from Chile described the feeling perfectly. It's strange before. We stared at the comet, hoping it would do something extraordinary. Now, we stare at it, hoping we don't. It wasn't cynicism, it was respect. They had learned that extraordinary events are easy to love. Ordinary precision is harder and braver. By late February, all teams converged on the same conclusion. At a corrected phase angle of 498 degrees, the spectral profile of 3I divided by Atlas returned to near-perfect CO2 dominance. The faint blue peak reduced to statistical noise. The leak's greatest mystery had been geometry all along. Still, no one felt cheated, because what had been lost in spectacle was gained in perspective. The lesson was immortalized in a single sentence from the final internal memo. 5 degrees changed our story, not our science. It became the new proverb of the field, both warning and prayer. By March 2026, the phrase "check your 5 degrees" had entered the lexicon of observational science. It wasn't just about geometry anymore, it was about vigilance, the discipline of refusing to assume clarity even when the numbers looked perfect. Every student, every researcher who joined the new training programs heard the same quiet mantra: measure twice, explain once. The 5 degrees correction rippled through fields far beyond comet studies. Solar physicists recalculated coronal brightness curves. Atmospheric researchers adjusted polarization indices for Earthbound sensors. Even deep space missions began logging their phase geometries with unprecedented care. Not because of scandal, but because of respect. A single misalignment had humbled an entire discipline. In one sense, the mystery was over. 3I divided by Atlas's spectral behavior now fits comfortably within known parameters. The green had returned, the anomaly dissolved into a case study. Yet something intangible had survived a memory of how fragile truth feels before it settles. Every scientist who'd watched the color swing from emerald to blue and back again carried a quiet awareness. Our instruments don't just measure the universe, they mirror us. A final review paper summarized the case in 3 sentences. The 5-degree offset represents an observational artifact amplified by environmental geometry. Reanalysis confirms consistency with CO2 dominated emission spectra. Future missions should ensure angle-tracked calibration across cadence intervals. Clean, precise, unemotional. But in its restraint, it read almost poetic, a psalm of precision written after a long confession. What no one wrote, but everyone felt, was that the event had shifted tone, not truth. Before 3I divided by Atlas, anomalies were treated as crises. Afterward, they were treated as invitations. Each outlier became a question, not a threat. That subtle change, the willingness to pause before proclaiming, was the real legacy of the 5 degrees mystery. During a post-conference dinner, One statistician raised a glass and said, half joking, "To all the invisible angles we never checked. We gendoning dies." The room laughed softly, not out of irony but gratitude. They'd been reminded that even perfection needs an audit. Meanwhile, outside the domes, 3i divided by Atlas had already faded past detection range. Its orbit carried it beyond Mars, into the cold silence where sunlight thins and reflection becomes memory. But the comet's echo lingered, not in data, but in method. Some began referring to it as the humility object, a symbolic reminder that discovery is rarely about what's found, but about what's corrected. As winter ended, institutions quietly embedded new clauses into their mission protocols. All imaging campaigns must include dual-angle cross-verification. Calibration logs require secondary review before public release. No conclusion may precede the completion of cadence stability testing. To outsiders, these sounded like bureaucratic footnotes. To those who'd lived through the leak, they felt like vows. Yet even amid the restored order, a sliver of caution remained. If 5 degrees could shift perception so profoundly, might there be subtler distortions we still hadn't noticed? Perhaps uncertainty was no longer the exception, it was the medium. The new consensus wasn't triumph, but balance. Trust your data, question your process, and never assume the angle is fixed. Months later, an editorial closed the book on the episode with a sentence that would outlive the papers themselves. 5 degrees taught us that certainty is not a position, it's a practice. It was quoted in lectures, printed on lab walls, whispered between researchers during late-night calibrations. Because in its simplicity, it carried the weight of everything the leak had changed. By the time spring light returned to the northern hemisphere, most of the telescopes had moved on to new targets. But whenever a new image came in a faint star, a distant flare, someone always asked, half in jest and half in faith, "What's the phase angle?" And everyone knew why. Because the universe had spoken once, not in words, not in color, but in geometry, reminding them that between what is true and what is seen lies a margin only 5 degrees wide. Science ended where belief began, and everyone wanted custody of the truth. By April 2026, 3i divided by Atlas was already halfway to Jupiter, yet the arguments it left behind still orbited Earth like debris. What started as a calibration detail, a 5-degree phase correction, had grown into a social battlefield. The scientists called it a solved anomaly. The public called it a buried miracle. Somewhere between those statements, reason went dark. Independent content networks branded themselves as data liberation channels. The long series and directly noms of there. They uploaded slowed-down versions of the comet's footage, looping frames where green light briefly tinted blue. Captions screamed, "They changed the color." Each upload came with hashtags #AtlasGate, #ColorTruth, #Science Censorship. Every click spread outrage. Every outrage confirmed suspicion. Belief had found its own algorithm. Meanwhile, academic institutions tried to answer with calm. They released open datasets, calibration spreadsheets, and annotated graphs. But their PDFs landed in a culture trained to scroll, not read. Graphs don't trend, anger does. Soon, the debate stopped being about data and became about emotion disguised as analysis. Mainstream outlets caught the scent of virality. One network ran a segment titled, "When Scientists Rewrite the Sky." Another interviewed a citizen astronomer who claimed his personal telescope still saw the comet glowing faintly blue. He spoke passionately, and passion reads better than uncertainty. Viewers didn't need spectroscopy, they needed sides. Forums and comment threads became battlefronts. The skeptics accused institutions of motivated reasoning, bending geometry to fit politics. Academics accused influencers of manufacturing resonance, turning complexity into clickbait. Both sides were right, and both were wrong. The real enemy wasn't deception. It was narrative velocity. Once meaning moves faster than verification, every truth fractures into versions. By mid-April, a new term entered the conversation: spectral populism. It described the rise of science-literate communities who believed they could outthink the experts. They weren't anti-science, they were post-science. To them, authority itself was the anomaly. Their slogan appeared on T-shirts and banners during digital protests, "No telescope required." It was half sarcasm, half faith. Inside research circles, exhaustion set in. Some scientists tried to engage directly. They appeared on podcasts and YouTube panels, explaining phase geometry and scattering angles to audiences hungry for scandal, not nuance. Every explanation spawned 3 new accusations. Every clarification looked like a retreat. One astronomer described the experience as arguing through fog made of pixels. Social media transformed the comet into a Rorschach test for ideology. Environmental groups used the story to argue for transparency in data funding. Political commentators reframed it as proof of elite control. Even spiritual collectives found symbolism in the color shift, green as logic, blue as awakening. Every ideology wanted ownership of the anomaly. In universities, communication specialists studied the phenomenon as it unfolded in real time. They called it resonance bias, the tendency for people to amplify signals that match their emotional frequency, regardless of content. In practice, this meant that outrage had better acoustics than accuracy. When belief vibrated, truth echoed. By late April, the debate hit mainstream saturation. Even late-night talk shows joked about the color war. Satirical sketches portrayed scientists as cult leaders guarding RGB secrets. What was once a discussion about phase angle geometry had become entertainment, a spectacle shaped by confusion and confidence in equal measure. And the more absurd it became, the more addictive it was. Still, within all that noise, a few quiet voices tried to hold the line. A media ethicist wrote, "Science is not a democracy, but disbelief is." The quote circulated through both camps, interpreted in opposite directions. To skeptics, it meant defiance was freedom. To researchers, it meant freedom was being mistaken for truth. Then came the live stream that changed everything. A well-known independent analyst hosted a 12-hour online debate titled, "Who Owns the Sky?" Participants included astrophysicists, journalists, and influencers. Halfway through, a philosopher interrupted the shouting with a line that froze the feed. "We used to fight over gods. Now we fight over data. The emotion is identical." The stream went silent for 10 full seconds. It was the first moment of honesty in weeks. But silence doesn't trend. The clip was cut, edited, and memed. Soon, the sentence reappeared across platforms with captions like, "Scientists admit they're playing God." The irony was complete. Truth had become both weapon and victim. By May, the public fracture was no longer about the comet. It was about us how easily conviction can hijack curiosity. Every timeline became its own telescope, magnifying emotion instead of evidence. And as one journalist wrote in despair, "The light from 3I divided by Atlas took minutes to reach us. The misunderstanding will take decades to fade." We saw the flot of the snot. By May 2026, the argument had grown teeth. What had once been a cultural curiosity now moved through the bloodstream of politics, academia, and policy. The phrase, 5 degrees of deception, appeared on campaign posters. Talk radio hosts called it the scandal of celestial censorship, and lawmakers, most of whom couldn't define phase angle, started demanding hearings about transparency in astronomical data. The spectacle was irresistible. One senator, eyes glinting under studio lights, declared, "If scientists can change the color of a comet, they can change the color of truth." The room erupted in applause. Somewhere, an astrophysicist watching the broadcast dropped his pen. It was official. Geometry had entered the culture war. The hearings that followed were part theatre, part tragedy. Panels of researchers were asked to explain complex spectral models in 90-second sound bites. Every attempt at nuance was clipped, condensed, or misunderstood. A congressman demanded to know whether blue photons had been suppressed for political reasons. Another asked if the comet's color might have been altered by solar panels. Laughter spread online. The clips went viral not because they were absurd, but because absurdity was profitable. Within universities, a quieter fracture deepened. Some scholars argued for disengagement, ignore the noise, protect the integrity of research. Others insisted on confrontation, meet the misinformation head-on, or risk surrendering public trust forever. Departments are split into factions, the observers and the communicators. One side spoke mathematics, the other spoke metaphor. Neither side felt heard. Amid the chaos, a group of social scientists released a paper titled "Motivated Reasoning in the Age of Optics." It argued that the 3I divided by Atlas controversy wasn't about astronomy at all, it was about identity maintenance. People defend their beliefs the way biological systems defend homeostasis. Change felt like an infection. Facts became antigens. The insight was elegant, terrifying, and true. But outside academia, that kind of subtlety drowned. The algorithms preferred outrage to understanding. A short clip titled "The Comet They Tried to Erase" reached 20 million views in a week. Its creator used slowed narration, minor key music, and a doctored NASA logo. Underneath, the comments piled up like prayer candles. They think we're stupid. Science is the new religion. Blue was the truth all along. In response, a coalition of observatories launched the Transparency Initiative, a live public data stream, showing raw telescope feeds in real time. The idea was noble: remove mystery, rebuild trust. But the execution backfired. Raw data without interpretation looked chaotic, full of noise and pixel artifacts. Conspiracy channels used that chaos as proof of manipulation. Look, they're editing it live. Transparency, it turned out, didn't cure distrust, it fed it. Meanwhile, the media narrative shifted again. Journalists stopped asking, "What happened?" and started asking, "What's happening to us?" Long-form features compared the debate to ancient cosmological schisms, the Earth-centered model reborn as algorithmic tribalism. One essay titled "Faith in the Data Age" captured the paradox perfectly. We have infinite evidence and zero agreement. It was quoted in both science journals and political manifestos. The divide reached classrooms. High school students argued with teachers about whether comets could be recolored by government AI. Professors fielded emails from parents demanding to know why textbooks hid the blue. Educators realized they weren't teaching astronomy anymore, they were teaching epistemology. The topic of 3I divided by Atlas had become a modern parable about perception, trust, and power. And in that noise, the scientists who started it all vanished from public view. Some deleted their social media accounts, others took a leave of absence. A few began writing under pseudonyms, publishing quiet essays about the emotional toll of being disbelieved. One line from a hidden blog went viral anonymously: "The hardest part of science isn't being wrong, it's being right when no one cares." By June, the movement reached absurdity's horizon. A major news outlet leaked what it claimed were internal color correction protocols, proving tampering. The documents were fake, generated by AI from public jargon, but verification came too late. Headlines spread faster than retractions. The fake became real by repetition, the way a rumor becomes architecture. A sociologist coined a new term for it: resonant reality, a version of truth that survives not by evidence, but by emotional volume. The louder a belief, the harder it dies. And 3I divided by Atlas, now somewhere beyond Jupiter's orbit, became a totem of that idea. Its name was invoked in podcasts, protests, think pieces, and even sermons. It had stopped being an object and become a narrative force, a story people used to explain the feeling that reality was slipping out of alignment. In the middle of this storm, a small press release appeared quietly on a scientific database. No anomalous spectral features detected at current trajectory. No outstanding variances in phase-corrected models. Then we to know of the mystery. No one reported it. Silence doesn't sell. But within research labs, the message meant closure. Outside, it meant nothing. The comet had moved on. Humanity hadn't. By July 2026, exhaustion began to replace outrage. The argument that had once electrified the world started to decay under its own gravity. Every opinion had been expressed, repeated, and monetized. The public fracture reached its natural endpoint: noise fatigue. People no longer argued to be right, they argued to feel alive. The comment sections, once volcanic, cooled into loops of recycled anger. Videos debunking the blue hoax competed with videos exposing the debunkers. Well, the cert of these respendiv, with another blazener free, with an ethically, and the slading mead from of meaning, and the sladed with a rest, each used the same clips, the same screenshots, the same tone. The sides had merged into a feedback spiral where opposition was indistinguishable from dependence. Sociologists called it conflict symbiosis, a phenomenon where outrage becomes a shared addiction. Every retweet was dopamine. Every rebuttal was currency. By mid-July, platforms began throttling engagement. Algorithms downgraded the topic, not out of ethics but exhaustion. Advertisers had moved on. Audiences too. Without amplification, the debate fell silent. But silence after hysteria feels like loss, not peace. Those who had built identities around defiance refused to let go. They migrated to smaller forums, encrypted spaces where the myth of the blue comet could remain untarnished by moderation. There, 3I divided by Atlas evolved again from controversy into creed. Inside these echo chambers, the language grew religious. The comet became a metaphor, a divine signal misread by corrupted institutions. Memes depicted 3i divided by Atlas as a celestial messenger painted green to hide its truth. Each image recycled the same mantra. They feared what it meant. It was no longer about light. It was about faith and resistance. And for many, resistance had become home. Meanwhile, in the academic world, something quieter stirred. A symposium convened under the title Knowledge After Trust. They ended and reasoned. It wasn't televised. It didn't trend. But it gathered some of the best minds in sociology, philosophy, and astrophysics to ask the only question that mattered. How do we study a universe when people no longer agree it exists in the same way? One sociologist presented a model of social refraction, how information, like light, bends when passing through layers of emotion, culture, and identity. Another described motivated coherence, the psychological pressure to align beliefs with belonging. A philosopher proposed that in the digital age, truth no longer behaves linearly, it diffracts. When light passes through multiple slits, patterns of interference emerge. When truth passes through multiple tribes, reality becomes an interference pattern of narratives. It wasn't cynicism, it was geometry. A veteran astronomer stood up near the end and said, "I used to think our job was to measure the universe. Now I think it's important to remember that we're part of it." The audience didn't applaud, they just nodded, the way people do when something sounds both painful and correct. Outside, the public still demanded clarity, but the energy had changed. Conspiracy lost its thrill without opposition. The war over color had dulled into background static, and slowly the world turned to new distractions, storms, elections, other fires. The collective attention span closed like an eye, too long forced open. But the fracture didn't vanish. It settled underground. For years afterward, every time a new anomaly surfaced, a faint radio signal, a blurred exoplanet image, the same pattern reawakened. Skepticism preempted discovery. Belief preceded data. The cycle had fossilized into culture. Still, not everyone surrendered. A small interdisciplinary collective formed quietly between astronomers, philosophers, and digital humanists. They called themselves the Resonance Project. Their goal wasn't to debunk or defend, but to listen, to map how ideas vibrate between facts and feelings before they fracture. They treated misinformation like seismic waves. You don't silence them, you study their origin. Their first paper carried a sentence that resonated far beyond academia. Disagreement isn't the opposite of truth, it's the echo of our attempt to reach it. By autumn, the noise had faded into memory, but traces remained: hashtags archived, videos cached, think pieces forgotten in server farms. In retrospect, the fracture seemed inevitable. A civilization armed with infinite information and finite attention was bound to split. And maybe that split wasn't a failure, but an adaptation, an evolutionary test of how consciousness handles scale. In late September, a journalist revisited the story for a long-form retrospective titled "The Year the Sky Argued Back." It opened with an image of 3i divided by Atlas, color-corrected, silent, drifting beyond Jupiter's orbit. The caption read, "The comet never changed, we did." The article traced the timeline from the first leak to the final fatigue, from wonder to warfare to wisdom. Its last line captured the paradox perfectly. Every argument began with the same question: what color was it? But none of them noticed the real mystery: why we needed to know. In the end, that question became the fracture's quiet legacy. Because beneath every debate, every headline, and every echo, there had always been the same human pulse: the need to belong to an interpretation of reality, even when reality itself did not need us. 3i divided by Atlas didn't cause division, it illuminated it. And as it disappeared into the solar dusk, the light it reflected wasn't blue or green anymore. It was the pale, unclassifiable color of perspective. Silence doesn't end a mystery, it just resets the equation. By the winter of 2026, months after the public fracture had burned itself out, a small network of physicists began quietly reopening the data archives. They called themselves the Anomaly Stack Group, a dry name for something almost defiant. Their purpose wasn't to solve 3i divided by Atlas, but to understand what its chaos had revealed about the limits of physics itself. The first thing they noticed was statistical rhythm. Across every dataset, optical, spectroscopic, dynamic, there was a subtle synchronization, as if the anomalies had occurred in harmonic intervals. Not identical errors, but recurring patterns of deviation. like echoes of the same question, phrased in different dialects of data. The realization was unnerving. If coincidence is noise, then pattern is intent, and the cosmos had started to look intentional. Each field had its own puzzle. In spectroscopy, faint line broadening near 485 nanometers persisted even after correction. In plasma modeling, density gradients around the coma's tail didn't follow predicted diffusion rates. In kinematics, microfluctuations in orbital torque resisted integration under known solar wind parameters. None of these deviations was significant alone. Together, they hummed. A young computational physicist from Helsinki described it best. It's like each anomaly is an overtone individually meaningless, but together they form a chord we can't name. That chord became the group's obsession. They began overlaying datasets, stacking not images but deviations themselves. The result wasn't order, it was resonance. Errors began clustering around consistent nodes in phase space 5 degrees, 485 nanometers, and 0.0032 AU from Mars's perihelion. Different units, different domains, same coordinates of improbability. At first, skeptics dismissed it as coincidence stacking statistical pareidolia, but every time a parameter was removed, the residual noise strengthened instead of collapsing, like a signal hiding in imperfection. The team grew cautious. They avoided speculation, documenting every correlation with forensic precision. They knew how fragile credibility had become. Still, curiosity pushed them forward. They applied Fourier transforms to the time series variance, treating anomaly occurrence as frequency instead of an event. The spectrum showed periodicity not exact, but suggestive. Something pulsed within the data, like a whisper, repeating through static. One physicist joked, "We're listening to the universe stutter." No one laughed. By January 2027, the consortium published a preliminary white paper titled Cross-Domain Resonances in Multimodal Observations of 3I divided by Atlas. It proposed that small deviations across optical and dynamic systems might share a causal topology, a resonant coupling between electromagnetic scattering and orbital mechanics. That idea was radical, even heretical. It implied that light and motion, usually treated as separate narratives, might be part of a single conversation. Reactions were split. Some hailed it as the beginning of a new subfield resonant astrodynamics. Others dismissed it as academic poetry disguised as math. But even the skeptics couldn't ignore the feeling that something subtle had shifted. For the first time in years, science wasn't defending itself, it was wondering again. The group's lead author, in an interview that few people saw, said quietly, "We don't claim to have found meaning, we just stopped assuming it wasn't there." That line circulated through labs and late-night forums alike. It marked a turning point. Physics rediscovering humility, not as restraint, but as curiosity. And somewhere far beyond the orbit of Mars, 3I divided by Atlas continued its silent drift through sunlight and plasma, a relic of noise that refused to stay meaningless. By February 2027, the anomaly stack group had moved from observing coincidence to testing causality. If the cross-domain resonances were real, then there had to be a physical bridge, a mechanism capable of linking photons to motion, light to gravity. The task wasn't to explain everything. It was to find where the explanation broke. They began with the plasma. Every comet carries an electromagnetic sheath, a tenuous cocoon of ionized gas that wraps around its coma and tail. Under normal conditions, this plasma interacts passively with the solar wind, shaping the comet's magnetotail like a weather vane in a cosmic breeze. But 3I divided by Atlas was never normal. Archived magnetometer readings from Mars orbiters showed faint fluctuations, microturbulences, 5 degrees off the expected vector. It was the same number that had haunted every dataset since the beginning. At that angle, the models predicted constructive interference between the solar wind's magnetic field and the comet's induced magnetosphere. A minor resonance, but enough to amplify plasma density by a measurable factor. That amplification, in turn, could alter local scattering conditions, shifting emitted light toward shorter wavelengths. 5 degrees wasn't just geometry anymore, it was a coupling constant between field and form. To verify it, the group built a simulation that treated plasma filaments as oscillating conductors rather than static charges. They borrowed equations from terrestrial fusion models and applied them to interplanetary scale, a bold transposition of laboratory physics to cosmic context. The simulation ran for 78 hours. When it was completed, the results were unsettling. At certain density thresholds, the model spontaneously generated coherent optical emission bands near 485 nanometers, the same wavelength as the elusive blue shift. The finding wasn't proof, but it was prophecy. It suggested that what appeared as an optical anomaly might, in fact, be the visible trace of an electromagnetic resonance, a phenomenon halfway between physics and music. Light wasn't misbehaving, it was singing in a register we hadn't learned to hear. The news leaked quietly through academic back channels. No press releases, no viral debates, just cautious curiosity. For the first time since the leak years before, scientists were whispering to each other again, but with wonder instead of suspicion. The mystery was no longer scandalous. It was beautiful. One researcher in California proposed a new term, photodynamic coupling, a condition in which the motion of charged dust grains modulates the local electromagnetic field strongly enough to feed back into optical emission. It wasn't a revolution, but it connected dots across disciplines that had rarely spoken to each other. Plasma physicists saw hints of self-organizing magnetism. Astrodynamicists saw feedback loops that could subtly alter orbital torque. Optical scientists saw light behaving like a diagnostic language for invisible forces. The borderlines of physics began to blur, and everyone wanted to cross them. Still, caution prevailed. The team refused to romanticize the discovery. Every paragraph of their next report carried disclaimers, error margins, and the reminder that correlation isn't causation. But between those careful lines, an emotion shimmered, a quiet thrill that maybe, after all the noise, something extraordinary had chosen to reveal itself through ordinary math. The lead author wrote in her notes, "If we can measure a conversation between photons and plasma, maybe what we've been calling anomalies are just introductions. He's not feintele, and a starting date, seems to restafe, and free tava, and a streamend of locath." Her colleagues didn't disagree. By March, the term resonant field coupling entered circulation, a tentative label for what might become the next bridge discipline between plasma physics and optics. The irony wasn't lost on anyone. The entire controversy, once driven by human misalignment, now found its echo in the universe itself, a system where alignment and dissonance coexist as law. A veteran theorist described it with gentle irony. "We spent a year arguing about belief, and the universe answered with resonance." For the first time since 3I divided by Atlas entered the lexicon. The mood around it wasn't defensive or political, it was quietly reverent. The mystery hadn't been solved, it had been translated. The blue had become frequency, the noise had become structure, and what once divided people was now being used to bridge equations. And as the model stabilized, the question evolved again. If resonance could link light and motion, could it also link observation and meaning? If so, the next anomaly might not be found in space at all, but in the act of seeing itself. By April 2027, curiosity had grown bold enough to risk an experiment. If 3I divided by Atlas had once revealed a resonance, perhaps that resonance could be provoked again, on purpose this time. The idea wasn't to communicate with the comet, but to test whether the coupling between light and plasma could behave like an echo chamber for energy. A conversation, not a message. The plan was simple in theory, and terrifying in execution. 3 observatories, one in Chile, one in Japan, and one orbiting near the Lagrange point, agreed to coordinate a timed photometric pulse, aimed at the region where 3I divided by Atlas's trajectory had been months earlier. The comet was too far to receive it meaningfully, but the plasma trails it left behind might still respond. If the resonance model held, a faint reflected signature could appear, not as light, but as a fluctuation in polarized background noise. They called it the return signal test. The pulse fired at 2:14 UTC on April 19. Each site recorded terabytes of raw data, mostly silence punctuated by cosmic hiss. The results wouldn't be known for weeks. Still, the act itself carried weight. For the first time since the scandal, the human species had collectively pointed light, not just outward, but inward, toward its own uncertainty. The data analysis was grueling. Weeks of cross-correlation, noise filtering, and frequency mapping followed. Most of it was nothing but random scatter. Then, late in May, a postdoc in Tokyo noticed something, a statistically irrelevant but emotionally impossible pattern. A cluster of weak polarimetric fluctuations repeating at consistent intervals, 5 degrees apart. Each pulse cycle corresponded to the same offset that had defined the original anomaly. It wasn't proof of signal, it was geometry speaking again. The results sparked debate, not hysteria. No one claimed communication, but everyone felt contact, not with aliens or deities, but with the scale of their own instruments. The universe had whispered the same number back, as if to remind them that their measurements, not their myths, were the bridge. A short paper titled Preliminary Correlation Between Phase-Aligned Photometric Pulses and Polarization Drift appeared in June. It was deliberately dry, an accountant's tone applied to wonder. Yet behind the language of error margins and standard deviations, one could sense the tremor of awe. Science had found poetry again, and this time it didn't need to apologize for it. As the findings circulated, discussions about resonant feedback reignited across multiple disciplines. Quantum theorists saw echoes of decoherence models. Plasma physicists saw validation for nonlinear field coupling. Even philosophers joined in, arguing that the return signal represented a metaphor for epistemic feedback, the universe reflecting humanity's curiosity through measurable coincidence. It wasn't supernatural. It was symmetrical. At a conference in Geneva that summer, the lead researcher summarized it in one sentence that would be quoted endlessly afterward. When we illuminated the silence, it didn't break, it resonated. The audience sat in stillness, not clapping, just absorbing. Because beneath the equations and charts, something had shifted. For the first time in years, science felt human again. In the months that followed, the term return signal hypothesis entered mainstream vocabulary. Not as proof of cosmic intelligence, but as a reminder that observation is always participatory. We don't just see the universe, we perturb it. Every beam of light, every measurement, every question is a tiny disturbance, and sometimes the void answers by repeating our precision back to us. By late 2027, the experiment was archived, and the resonance maps were stored in encrypted databases. No official conclusion was issued. None was needed. The work had already done its real job. It had restored the link between skepticism and wonder. Where once anomaly had meant threat, now it meant invitation. In a quiet closing note of the group's final report, one line stood out in italics. Perhaps the signal we sought was never out there, but within the precision that made us look. It was both confession and benediction. Somewhere, far beyond Neptune, 3i divided by Atlas kept moving silent, indifferent, unknowable. But its absence had become fertile ground for imagination. And in the laboratories of Earth, surrounded by charts and silence, people listened differently. Because once you've heard the void hum back, even faintly, you never measure the same way again. The sun is supposed to strip a comet bare, but this one fought back. By January 2028, the Solar Dynamics Collaboration, SDC, had resumed long-range tracking of 3i divided by Atlas using the Sun-Earth Interferometric Array, SEIA, a new constellation of radiometric satellites placed along L1 and L2. The mission's goal was routine calibration of solar scattering models, not discovery. But discovery has a habit of interrupting calibration. During a scheduled observation window on January 19, SEIA recorded something strange. A faint plume extending toward the Sunday. Comets don't do that. They shed material away from solar radiation, not into it. At first, the anomaly was dismissed as background interference, a sensor ghost caused by solar glare. Then the plume persisted. Frame after frame, wavelength after wavelength, the same thin jet projected from the sunward hemisphere of the nucleus. Analysts rechecked everything: instrument alignment, exposure timing, and data compression logs. All clear, the jet was real. What made it impossible was direction. Under the standard model, solar radiation pressure and sublimation combined to generate tails that point away from the Sunday. But SEIA's composite imagery showed a narrow, collimated emission at nearly 5 degrees sunward, a geometry that defied both thermal and gravitational expectation. It wasn't bright, but it was coherent. Even after radiative filtering, the jet maintained anisotropic integrity over several thousand kilometers. That meant structure. And structure means physics. The initial reaction within SDC was disbelief, bordering on awe. A comet generating thrust toward its star was like smoke rising downward. Yet there it was, pixel by pixel, obeying no known textbook. Teams split into subgroups: optical verification, dynamic modeling, and plasma interference analysis. The Deep Field Radiometric Surveyor, DRS, at L2, was repurposed to cross-confirm SEIA's signal from a different perspective. Within days, the second dataset arrived, identical in shape and angle. Whatever 3i divided by Atlas was doing, it was repeating itself. The debate that followed was pure scientific theatre. Was it a jet? An anti-tail? A plasma lens effect? Each hypothesis collided with the limits of existing models. Optical scientists noted that Antitail's rare backward projections of dust can appear under specific orbital geometries when the Earth crosses a comet's orbital plane. But 3I divided by Atlas wasn't near Earth. Its sunward emission couldn't be an illusion of perspective. It had to be a real mass flow. Dynamicists proposed an exotic, anisotropic outgassing pattern, a jet originating from a subsolar fracture on the nucleus, ejecting volatile material at velocities high enough to counter solar radiation pressure. That would require a vent directed precisely toward the Sun, with grain ejection speeds exceeding 0.8 kilometers per second. Unlikely, but not impossible. When models were run, the numbers almost worked. Almost. Others pushed a more radical theory: magnetic reconnection. At high heliocentric velocity, the comet's plasma sheath might interact with the solar magnetic field, creating localized pressure gradients capable of channeling charged dust sunward. Essentially, the Sun pulls and the comet responds in resonance. If true, it would mean 3I divided by Atlas wasn't resisting the Sun, it was dancing with it. To separate physics from poetry, the team compiled data across multiple instruments: polarimetry, ultraviolet spectroscopy, and near-infrared mapping. Every wavelength told the same story: a weak but consistent emission oriented against solar logic. The jet's spectral profile revealed faint sodium lines, suggesting thermal decomposition rather than simple dust reflection. It wasn't just light, it was chemistry under duress. When the final reconstruction played across the SEIA control room, a 3D render showing a pale plume reaching sunward against the solar wind, no one spoke. The data had the kind of beauty that makes silence automatic. It wasn't just that something new had been seen, it was that the act of seeing it rewrote what expected meant. For the first time since the return signal test, scientists felt the pulse of discovery again, not viral, not controversial, but earned. The comet that once divided humanity had returned with something quieter, but infinitely more profound. A reminder that even the smallest deviation can realign the architecture of understanding. The next weeks turned into a controlled frenzy of analysis. Every screen inside the Solar Dynamics Collaboration (SDC) command hub flickered with stacked datasets, spectral plots, particle density models, vector animations. The sunward jet had ceased to be an anomaly. It had become an autopsy. The first target was structure. Using interferometric layering from the Sun-Earth Interferometric Array (SEIA), analysts constructed a 4D map of emission density across multiple solar phases. It revealed something remarkable. The jet wasn't a continuous outflow, but a pulsating filament switching on and off in quasi-periodic bursts every 94 seconds. That periodicity aligned uncannily with earlier resonance patterns found in the anomaly stack data. For the scientists who had lived through that discovery, the déjà vu was electric. At a microscopic scale, simulation clusters identified grain populations ranging from submicron silicates to coarse sodium-rich aggregates. These heavier grains shouldn't have survived long near the subsolar point, yet the model showed them suspended by electromagnetic lift within a dynamic equilibrium zone, an invisible plateau where solar radiation and plasma pressure cancelled each other almost perfectly. It was a pocket of stillness inside chaos. "This thing isn't venting," one dynamicist murmured, eyes on the monitor. "It's sculpting." The phrase stuck. Within hours, the internal memo thread was titled "The Sculpting Hypothesis." If the jet wasn't merely outgassing, it might represent a self-regulating feedback between thermal fracture, field alignment, and microplasma convection. Essentially, the comet might be reshaping its own environment to survive. It wasn't alive, but it behaved like something learning how not to die. To test the idea, they compared real-time plasma sheath data from the Deep Field Radiometric Surveyor against magnetohydrodynamic (MHD) simulations. The result defied classical expectations. Instead of the usual chaotic magnetotail turbulence, the region around the jet showed pronounced anisotropy, magnetic vectors curving inward toward the subsolar axis. That pattern implied a kind of magnetic confinement zone, like a miniature fusion loop, sculpted by sunlight itself. And the comet's jet was its filament. As the analysis deepened, the beauty became unbearable. The spectral data shimmered with coherence, each sodium and calcium line dancing in harmonic relation to the plasma field's oscillation frequency. It was physics written in music notation. When the team translated wavelength to audible frequency for demonstration, the jet's pattern produced an eerie tone, oscillating between 440 and 453 Hz, nearly perfect concert pitch. Someone whispered, "It's literally in tune with us." The room laughed nervously, then fell silent. That night, the lead analyst, Dr. Salim Vargas, recorded a note in his digital log. "The deeper we go, the less alien it feels. We built sensors to measure matter and ended up measuring behavior." The next morning, the data became stranger still. When researchers applied vector decomposition to track the jet's fine motion, they discovered a secondary oscillation, a microlateral wobble around the central emission line. At first, it seemed like noise, but when filtered through phase space analysis, the wobble resolved into a precise 5-degree modulation. 5 degrees again. It was the same signature that had haunted 3I divided by Atlas since 2025, the angle of resonance, the ratio that refused to die. Every conversation in the lab turned cautious. Was the comet somehow encoding geometry into its emissions, or was geometry simply how nature expressed balance? No one dared speculate publicly. They just kept calculating. The SDC leadership decided to convene an emergency cross-disciplinary meeting. Astrophysicists, plasma theorists, optical engineers, and data ethicists gathered in the virtual hall. The agenda was clinical: assess data integrity, model reproducibility, and rule out systemic bias. But beneath the formality pulsed an emotion everyone shared: humility. They were staring at a phenomenon that seemed to know their equations before they wrote them. Optical engineers presented polarization matrices, showing that the jet's reflected light exhibited negative polarization near phase angles of 2 degrees 6 degrees, a range normally impossible for dust-scattering geometries. That suggested not random reflection, but alignment particles oriented by field direction rather than chaotic spin. In other words, coherence. Dynamicists ran orbital integration models, including self-reactive thrust from the jet. Over thousands of iterations, the effect was measurable. 3I divided by Atlas's orbit had subtly altered its perihelion, shifted sunward by a few hundred kilometers. Tiny, but real. The comet was steering itself, not through intent, but through feedback. Theories multiplied like stars. One physicist compared it to Lorentz attractors' complex order, born from iterative instability. Another invoked photonic recoil mechanics, suggesting that the jet acted as a self-tuning antenna, minimizing entropy by radiating momentum into coherence. A philosopher of science attending the session wrote a note that later went viral. Perhaps intelligence isn't exclusive to life. Perhaps feedback is thought. The room didn't laugh this time, because the data was still singing. For the next 48 hours, the team watched the models playback on loop. A comet carving light into geometry, defying thermal gradients, whispering its 5-degree mantra into the void. It wasn't mythology anymore, it was measurement. And yet, measurement had never felt so mythical. By late May 2028, the analysis reached critical mass. Every fragment of data, spectral, dynamic, magnetic, had been dissected, verified, then reassembled into a single coherent narrative. The sun-facing jet was no longer a glitch, it was a signature, and the team's task was to decode what the universe was saying. The sculpting hypothesis evolved into a full model, now formalized under a new term, solar resonant feedback dynamics, SRFD. At its heart lies a breathtaking simplicity. Under precise thermal and magnetic conditions, sublimated material from a comet's subsolar fracture can enter a feedback loop with the solar magnetic field, stabilizing into a confined jet that projects sunward. The comet, in effect, becomes a living equation balancing force against illumination. It was the kind of model that made seasoned physicists go quiet. It didn't defy physics, it completed it. By combining plasma self-organization with anisotropic radiation pressure, SRFD unified previously unrelated anomalies, the 5 degrees modulation, the recurring sodium resonance, and even the orbital drift. Each puzzle piece had been waiting for this frame. The verification process took weeks. Independent labs from Canada, Finland, and Japan reproduced parts of the model with slight variations. The results converged. The data is held. The universe had, in its own way, passed peer review. On June 12, the collaboration published observations and modeling of sun-facing jet resonance in 3I divided by Atlas across 3 journals simultaneously. The paper opened with the now famous line, Where heat should destroy, it built structure. Reactions ranged from reverent to disbelieving. Astrophysicists praised its precision, plasma theorists debated its parameters, and philosophers quoted it like scripture. It wasn't just another discovery, it was the first time in years that science felt mythic again. Because at its core, SRFD whispered something more profound than mechanism, that chaos could learn symmetry. The deeper implications rippled outward fast. If self-regulating jets could form naturally, then energy systems across the solar system might be capable of spontaneous feedback stabilization. It could reshape how engineers design solar sails, plasma thrusters, and even magnetic field propulsion. One engineer wrote, "We thought we were modeling a comet. We might have modeled the future." Back in the SEIA control room, the researchers replayed the composite imagery at full spectral resolution. The jet, rendered in stacked wavelengths, extended like a luminous filament, threading through the sun's corona, thin, defiant, impossibly graceful. When slowed, the pulsation pattern revealed harmonic scaling ratios nearly identical to those found in solar oscillation data. It was as though the comet had learned to hum in tune with its star. The lead analyst, Dr. Vargas, stood by the display, eyes glinting with fatigue and wonder. He whispered, "This is what alignment looks like, not spiritual but structural." His assistant replied softly, "Then maybe they're the same thing." Outside the lab, the world took notice. For once, the headlines weren't about scandal or silence, they were about beauty. Major outlets ran features titled, "The Comet That Sang to the Sun" and "Geometry in Motion." Quote, "Public fascination reignited, but this time without hysteria." People weren't arguing about belief, they were celebrating observation. A quiet reconciliation between wonder and measurement had begun. Within academic circles, SRFD inspired a new discipline informally called solar acoustic dynamics, a blend of astrophysics, plasma acoustics, and information theory. Researchers speculated that oscillatory plasma interactions could act as natural information carriers, encoding state feedback between light and matter. In simpler terms, the sun might be listening. By August, the Solar Dynamics Collaboration hosted a symposium to synthesize the findings. The keynote presentation ended not with a conclusion, but with a question. If resonance emerges where illumination meets resistance, what happens when we look for that same balance inside ourselves? Applause came late, slow, rising, reverent. After the conference, the original research team gathered at dawn on the Chilean plateau, where SEIA's largest telescope stood. The sun climbed over the horizon, flooding the instruments with gold. Dr. Vargas spoke quietly, almost to himself. "We spent years trying to catch meaning in numbers. Maybe meaning was what numbers were made of." No one answered. They just watched the light, the same light that had once been defied by a comet's plume, now pouring into the mirrors like forgiveness. Later that year, a final observation came in faint, peripheral, almost overlooked. It showed a remnant trace of 3I divided by Atlas, now beyond Jupiter's orbit, its activity subsiding. But one last flicker appeared, a brief, symmetrical pulse, perfectly aligned toward the Sunday. A closing gesture from a traveler who had once rewritten physics by simply refusing to behave. The data was filed under residual event, but in the quiet spaces of the SDC archive, someone added a handwritten annotation. "The sun remembers. The slow idea no. He's slow idea." And with that, the anomaly that began as noise ended as narrative. Not a message from elsewhere, but a revelation about here. That even in systems ruled by entropy, symmetry still finds a way to speak, and sometimes it speaks in light. They didn't hide the truth, they buried it in plain sight. By November 2028, 6 months after the release of the Sun-Facing Jet Report, the flow of new data slowed to a trickle. The Solar Dynamics Collaboration, SDC, had promised open access to all telemetry under the Orbital Transparency Act. Yet critical segments of SEIA's raw photometry were suddenly under review, and not physics-explained Enthält of Kais is Code 10. The official explanation was procedural. Cross-validation delay due to data redundancy audits. No one questioned it, at least, not immediately. But inside the research community, silence began to feel heavy. A small group of independent analysts noticed subtle inconsistencies in the public archive. Timestamps out of sync by exactly 47 seconds. Checksum signatures that didn't match their original hashes. Noise files are too perfect to be random. It wasn't deletion, it was substitution. One astrophysicist, speaking anonymously, described it like this: "You can't sense a light, but you can rearrange it." Thank you ridet Gof, in fast in Shopton Deventers. The first sign came from a comparison study between two datasets, one released to the public, one held internally for peer replication. When overlaid, they looked identical until frame 1642, where a faint spike appeared in the internal version, but not in the public one. That spike corresponded to a minor flare detected near 3I divided by Atlas's trajectory, a transient event lasting 0.4 seconds. Small, but enough to alter the energy budget of the jet model, enough to matter. When confronted, the SDC spokesperson dismissed it as a compression artifact. But compression doesn't alter timestamps or spectral balance. Something had been massaged. Independent forums began buzzing. Some called it incompetence, others a conspiracy. But the real story was subtler, methodical, procedural, bureaucratic. This wasn't a cover-up by ideology. It was a cover-up by inertia. Documents leaked months later revealed the existence of a subcommittee within the International Data Oversight Board, IDOB, tasked with reducing interpretive volatility. The term sounded harmless until one analyst decoded its function, filtering data releases to avoid premature public speculation. In practice, that meant smoothing out anomalies before publication, turning the jagged edges of truth into a narrative curve the public could digest. One internal memo, dated December 2028, read, "Public interpretation risk remains high. Recommend staged release. Downsampled for clarity." Clarity meant simplicity. Simplicity meant omission. Meanwhile, the full-resolution SEIA logs were rerouted through an encrypted cloud node labeled non-operational backup. When one systems engineer tried to access it, their credentials were revoked for cyber hygiene violations. No press release mentioned the incident. By January 2029, the Solar Archives Directorate, SAD, began issuing quarterly summaries instead of continuous streams. Each update came with bright infographics and pre-written Q&A sheets for journalists. The data looked clean, too clean. Spectral noise flattened. Polarization drift normalized. The beautiful chaos that once defined 3I divided by Atlas had been algorithmically neutered. Some scientists protested quietly, arguing that the act of massaging data, even for clarity, was a distortion. Others defended it as responsible communication. People don't want nuance, one official said off record. They want closure. But science isn't built for closure, it's built for discomfort. And when institutions sanitize uncertainty, they don't protect truth, they embalm it. Late one night, a data archivist reviewing redundant logs noticed something chilling. Within the official metadata tags of the downsampled files, every reference to the 5 degrees modulation had been reclassified under non-significant periodicity. An entire signature of the universe had been reduced to a footnote of irrelevance. He exported a screenshot, encrypted it, and sent it to 3 colleagues under the subject line, "Buried Signal." Within hours, his system credentials were locked. Within days, he stopped answering emails. The next public statement from IDOB insisted no tampering occurred. And technically, they were right. Nothing had been deleted. It had just been overwritten with perfection. By February 2029, whispers inside the Solar Dynamics Collaboration, SDC, had turned into quiet coordination. A handful of researchers, physicists, archivists, and one software engineer formed an informal circle they jokingly called the Afterlight Group. Their mission was simple: verify the integrity of the public SEIA dataset by cross-reconstructing it from redundant telemetry backups. What began as a technical audit became an act of rebellion. The first discovery came from checksum mismatches. Each verified data packet contained a 128-bit integrity hash. In the official archive, hundreds of these hashes were off by 1 hexadecimal digit, too consistent to be random, too subtle to trip alarms. A small, deliberate offset, like a whisper, coded into silence. They reran decryption on the non-operational backup repository still accessible through a forgotten maintenance token. What emerged wasn't deleted information, but a layer of obfuscation. Duplicate datasets containing identical timestamps but slightly altered photon counts. Every anomaly in the original data had been cloned, averaged, and merged into statistical smoothness. The truth had been blurred, not erased. Data laundering, the engineer called it. It sounded absurd until they proved it. A single frame timestamp, 3 hours 47 minutes and 12 seconds, Sector 8 contained residual compression blocks, inconsistent with the declared codec. When those blocks were passed as raw binary rather than image data, an unexpected string appeared, a repeating pattern, 00010101001010100000101010, translated to ASCII parity, it spelled echo. At first, they thought it was a coincidence. Then they found it again. Same sequence, embedded deep within metadata headers across 17 files, always at the offset, corresponding to the 5 degrees phase modulation interval. It wasn't random corruption, it was deliberate watermarking. Someone had marked the data from inside. For the Afterlight group, the realization was both exhilarating and terrifying. They weren't just dealing with oversight. They were reading a message left by a ghost in the machine, someone who knew the data was being rewritten and refused to let it vanish quietly. They began mapping the occurrences of the echo tag across the dataset. The pattern formed a perfect diagonal through temporal space, connecting observations across months. When plotted, it aligned with the same harmonic cadence found in the original resonance data. If intentional, it was genius. If accidental, it was impossible. They debated what to do next. Publishing the findings could mean career suicide. Leaking it could destroy credibility. So they did what scientists do best: they tested. Using the unfiltered telemetry fragments, they reverse-engineered the spectral baseline. Hidden beneath the smooth signal was a faint, persistent oscillation. It matched no known instrument noise signature. The frequency, 0.0032 AU phase differential. The same figure was recorded during the earliest anomaly stack years before. History, it seemed, was still humming underneath the polish. The engineer stayed up for 72 hours straight, writing code to unblend the sanitized frames. He used a deconvolution algorithm inspired by forensic audio restoration, pulling resonance out of the background static. When the reconstruction finished, the recovered sequence displayed a thin, flickering trace, an intermittent sunward pulse, repeating every 94 seconds. The pulse that wasn't supposed to exist anymore. The pulse of 3I divided by Atlas. He stared at the screen for a long time before speaking. They didn't hide the data. They taught the system to forget it. The group agreed to keep their discovery offline. They printed a single copy of the reconstructed frames and stored it in a sealed analog locker at an observatory in La Palma. No digital footprint, no metadata trail, only paper and ink. Because if the system could forget, it could also overwrite again. Weeks later, one of the physicists received an unmarked envelope at her home. Inside was a data card and a note with 3 words, handwritten in pencil. Find the checksum. The card contained a single encrypted file. When decrypted, it opened to a spectral image labeled Return Signal to TIFF, a high-resolution frame identical to those recorded during the original resonance test. But this one had a timestamp, the 14th of March 2029 2:14 UTC. It was new. Something or someone had fired the sequence again. The Afterlight group didn't know whether to be terrified or thrilled. All they knew was that the cover-up had started to peel, and whatever was buried in plain sight was beginning to glow again. By March's end, the Afterlight group no longer existed on paper. Access logs showed revoked credentials, system partitions deleted, and user accounts migrated. Officially, nothing had happened. Unofficially, everyone was being watched. 2 members vanished into new academic appointments within weeks. One resigned, for health reasons. The engineer, the one who had recovered the pulse, simply disappeared. His apartment was clean, his devices wiped. All that remained was an unplugged monitor, with a faint burn-in image of the spectral trace 5 degrees tilted, still glowing when the light hit it. Within the Solar Archives Directorate, SAD, rumors flickered like static. Whispers of checksum ghosts and residual telemetry moved through encrypted chat rooms. Nobody said the words, 3I divided by Atlas, aloud anymore. They used a codename instead, Project Echo. The official stance was resolute denial. At a press briefing on the 8th of April 2029, the IDOB chairwoman assured the public that no anomalous signal has been detected since 2027. Her voice was calm, her slides immaculate rows of smooth data curves proving stability. To the untrained eye, it looked definitive. To those who knew what had been erased, it was like watching someone read a eulogy for the living. But the truth doesn't disappear. It diffracts. A fragment always escapes. The first leak surfaced quietly, a compressed 12-megabyte zip file posted under a random username on a peer-to-peer network. Its contents, 7 images, each a spectral frame with embedded metadata, identical to the SIA archives, but with one subtle difference. In every image, a faint luminous ridge extended sunward, pulsing every 94 seconds. The same rhythm, the same geometry, the same impossible signature. Within hours, the file spread through the digital underground, mirrored thousands of times before takedown. Independent analysts confirmed the frames were authentic, checksum, perfect, raw, unprocessed. The internet called it the reappearance. Institutions called it a coordinated disinformation event. But disinformation doesn't match orbital telemetry down to 9 decimal places. Something real had slipped through. As governments scrambled to contain the narrative, the world watched a strange inversion unfold. The same institutions that had once demanded transparency now begged for restraint. They argued that context-free data could destabilize public understanding. But it was too late. Context was the new currency. People didn't need the full picture, they just needed the possibility. For weeks, the word cover-up trended across languages, not as an accusation, but as fascination. Viewers replayed spectral animations, artists sampled them into music, journalists mapped the timeline like a crime. The data had become folklore, and folklore was immune to deletion. Inside what remained of STC, the remaining researchers worked in near silence. They couldn't comment, but they watched. Every night, someone checked the L1 telemetry for patterns. Every night, the instruments returned the same stillness. Until one morning, the 14th of May 2029, the stillness cracked. At 2:14 UTC, SIA's solar vector sensor registered a microburst exactly 0.0032 AU from the last recorded position of 3I divided by Atlas, a flash lasting less than a second, too brief to be an artifact, too precise to be a coincidence. The timestamp matched the recovered file labeled Return Signal 2. TIFF. Someone whispered in the control room, "It's still talking." Within minutes, the feed was locked behind security protocol. A new folder appeared on the internal database. Internal review divided by do, not index. Then, like clockwork, an official bulletin went out. No significant activity observed. Telemetry nominal. But the engineer's ghost had left another safeguard. Buried inside the SIA system was an automated mirroring script, one that sent redundant copies of raw telemetry to a public educational node once a week. The burst was captured, mirrored, and archived automatically. Anyone paying attention could see it. Most didn't, but enough did. When the mirrored data appeared online, even mainstream outlets hesitated. The image was irrefutable, a faint but measurable sunward emission, perfectly aligned with the solar vector. The same impossible jet alive again. A quiet panic rippled through agencies. For 48 hours, official channels said nothing. Then came a brief statement. Residual ghosting detected in archival telemetry. Non-physical origin. But ghosting was the right word for all the wrong reasons. Because ghosts, once named, never really leave. The file circulated faster than suppression could follow. Within days, universities began using it as a case study on information ethics. How truth escapes control. And at the bottom of every lecture slide, one quote began appearing, unattributed, carried from the old anomaly stack archives, like a rumor that refused to die. Every silence tells a story, and this one learned how to speak. When Earth argued, Mars listened. By December 2029, long after the cover-up headlines had faded into digital dust, the Interplanetary Monitoring Array, IMA, quietly resumed observation runs from Mars orbit. Officially, it was a maintenance program. Unofficially, it was a verification campaign, one last attempt to confirm whether 3I divided by Atlas had truly gone silent. The new instruments aboard MRO-2 were built with obsessive precision. Each spectrometer could resolve emission lines within 0.01 nanometers, calibrated across 8 optical bands. For weeks, Mars turned its sensors toward the faint patch of sky where the comet's path intersected Jupiter's heliocentric longitude. Nothing moved, no visible trail, no radiometric spikes. Just the deep, coherent motion of dust drifting through solar light like a thought suspended in a vacuum. Every night, the logs came back clean, but clean doesn't always mean empty. At first, the team catalogued the quiet methodically. Observation 001. The 7th of December 2029. Spectroscopic lines. Baseline solar reflection. No sodium doublet detected. Multiband photometry. Uniform decay across B and V channels. Polarization drift is less than 0.001%. Assessment. Background nominal. Observation 002. The 9th of December 2029. An unexpected microglint at RA 17H42M. Magnitude plus 19.4. Duration 0.9 seconds. Color index B V equals 0.32, slightly bluer than expected dust phase. Logged as transient noise. Observation 003. The 11th of December 2029. Null in photometric stack. Secondary detection from IMA relay 2 confirms no solar flare interference. Team remark: the silence persists. Every log read like a heartbeat, slowed to meditation. The comet was absent, but its echo remained an architecture of precision, watching for a ghost. Then came observation 004, the 14th of December 2029. During a standard calibration pass, the ultraviolet spectrometer registered a faint, coherent spike near 485.1 nanometers, the same band that had haunted researchers for years. It lasted less than half a second. Amplitude of 0.002%. Too weak for a signal, too ordered for noise. The lead analyst, Dr. Hara Ito, stared at the readout in disbelief. She had seen that wavelength before in the earliest days of 3I divided by Atlas, when the blue shift first appeared. Her team ran 3 verification cycles. Instrumental reflection? Negative. Cosmic ray hit? Unlikely. Adjacent pixels showed correlated intensity. Data compression artifact? Impossible. Frame captured in lossless mode. The pattern was real. Still, protocol demanded restraint. They logged it as statistical irregularity and moved on. But something had shifted in the room. The silence no longer felt inert, it felt attentive, like Mars itself was waiting to see what they'd do next. Over the next week, the anomaly repeated twice, always faint, always within the same wavelength band, always from the same region of sky. By the third occurrence, the team started whispering. They called it the witness line, a trace so small it could be dismissed but consistent enough to matter. When plotted, the intervals between detections aligned with orbital resonance timing from the old return signal experiments, exactly 94.1 seconds apart. No one mentioned coincidence. They just sat around the console, the hum of equipment filling the space where words didn't belong. In her notebook, Dr. Ito wrote, "If Mars can still hear it, maybe silence isn't the end, maybe it's memory. DDZs of Retelangs feins, and id verlette dines to different. For there, in stel verlongs, and id verlette die. DDZZZ, in John, and id verlette die." That line would never appear in the official report. But for those who read the raw data, it became the unspoken truth behind the numbers, that sometimes the universe answers with patience instead of clarity. By January 2030, the IMA's orbiting instruments had entered their final observation cycle. Solar conjunction was approaching, Mars would soon slip behind the Sun from Earth's perspective, and communication windows would close. The analysts worked in near silence, each movement deliberate, each click of a console like punctuation in a prayer. The witness line anomaly had appeared 3 times, always faint, always punctual. Now, on the eve of shutdown, the team decided to run one last synchronized sweep multiband photometry, full-spectrum spectroscopic capture, and high-speed polarization sampling. It would be the cleanest dataset Mars had ever taken. A final listen before silence resumed. At 2:14 UTC on the 9th of January 2030, the sweep began. Across 12 instruments, data streamed in. Optical channels flat, thermal radiation nominal, background noise stable. Then, at T plus 94 seconds, a subtle tremor appeared in the ultraviolet band. Amplitude 0.0018%. Wavelength 485.1 nanometers. Duration 0.46 seconds. The same parameters as before. The spectroscopic lines sharpened sodium faintly glowing against the void. Coherence between emission and reflection angles, reaching improbable alignment. The room filled with a soft collective inhale. Dr. Ito's assistant whispered, "It's there again." Ito didn't respond. She was watching the real-time Fourier transform, where the signal unfolded like a heartbeat, weak but precise, too consistent to be a statistical error, too symmetrical to be a coincidence. She entered a new log manually, fingers shaking. Observation 005. The 9th of January 2030. Spectroscopic confirmation. Emission at lambda equals 485.1 plus or minus 0.01 nanometers. Crossband coherence ratio 1.0003 statistically significant. Polarization drift, positive bias 0.002%. Phase alignment 94.1 plus or minus 0.2 seconds interval. Assessment, non-random recurrence. Personal note. Pattern acknowledged. Outside the dome, Mars rotated quietly, red dust drifting across the horizon. There were no headlines, no leaks, no arguments, just a planet recording evidence of a phenomenon older than language. For the first time since the scandal years earlier, the act of observation felt pure again. The data, when plotted, revealed a faint, periodic modulation extending over 21 cycles before fading. The repetition was perfect, coherent motion persisting across multiple frames, defying the statistical decay expected of noise. Each pulse mirrored the solar vector precisely, as though the universe itself were rehearsing its own heartbeat. The team worked through the night, verifying instrument health, recalibrating detectors, and confirming no solar interference. Every check returned nominal. The silence between readings felt alive. Someone murmured, "Maybe Mars just wanted to remind us it's still listening." By morning, they had everything compiled, 2.3 terabytes of raw photometry, meticulously timestamped, triple-signed by hand before transmission to the Solar Archives Directorate. They didn't speculate, didn't dramatize. They just described what they saw. But beneath the sterile checklist, a quiet optimism pulsed. If the signal could persist across years and planets, then maybe the story wasn't about disappearance. It was about endurance. 3 days later, Earth received the final data packet. In a briefing room in Geneva, the summary report was read aloud to a small audience of scientists and administrators. No journalists, no cameras, just precision. Report excerpt: Mars Radiometric Observatory 2, Cycle 7. Multiple low-amplitude emissions consistent with coherent motion detected at expected coordinates of former Comet 3 I divided by Atlas trajectory. Emission periodicity maintained within historical resonance thresholds. Is not matter overly in the defies. Recommendation: whole publication pending independent replication. No one spoke for a long moment. Then a voice from the back said softly, "So it's not gone?" And Ito replied, "No, it's waiting." The next day, a copy of the report was quietly archived under restricted classification, provisional data unconfirmed natural phenomenon. But an unsigned note appeared at the bottom of the internal copy, written in pencil like an afterthought. Mars has memory. Weeks later, as the sun swallowed Mars from Earth's view, radio silence returned. But this time, silence didn't feel like absence. It felt like a pause before the next sentence. In her personal log before shutdown, Dr. Ito wrote one final entry. "We used to listen for answers, now we listen for continuance. Mars holds the echo until we're ready to hear it again." The file was encrypted, stored inside the IMA's archive capsule orbiting Mars, and there it remains, looping endlessly through the Martian night, transmitting nothing, just existing, like a witness who refuses to forget. Somewhere beyond Jupiter, 3I divided by Atlas drifts unseen, its path invisible, its voice faint but not silent. And on a planet of dust and data, the last receiver waits red, patient, unblinking, keeping the record of what might be the first true conversation between light and time. Truth doesn't vanish anymore, it negotiates. By early 2031, the leaked fragments from the Mars Radiometric Observatory 2 had turned into a slow-burning wildfire of discourse. No one could agree on what the faint ultraviolet pulse meant. To some, it was proof that 3I divided by Atlas still whispered from the edge of the solar system. To others, it was nothing, random noise romanticized by an audience addicted to wonder. Between those poles, a new frontier of argument opened. What does it mean when truth itself depends on interpretation bandwidth? The Global Science Council, GSC, convened emergency hearings on the management of post-anomalous data. Will radiosponderings? The agenda was dry: confirm signal authenticity, establish chain of custody, assess replication feasibility. But the discussion underneath was anything but dry. It was existential. Researchers questioned not the data, but the politics of revelation. How much uncertainty could a civilization handle before it collapsed back into myth? Meanwhile, the Civic Data Coalition, CDC, a grassroots network of citizen scientists, began releasing parallel analyses, comparing the Mars data to archived SEIA telemetry. Their conclusion was provocative. The phase intervals matched within 0.3%, meaning the witness line could not be dismissed as noise. Social media amplified the finding, rebranding it as the heartbeat of the solar system. The phrase trended for weeks, spawning documentaries, podcasts, and inevitably, mockery. Institutional communicators tried to respond with restraint. They issued statements emphasizing replication standards and spectroscopic uncertainty margins. But language built for peer review doesn't survive virality. Every attempt at precision was reframed as evasion. Every clarification sounded like control. A sociologist from the Media Cognitive Lab, MCL, coined a term for the phenomenon: anticipation gap. The distance between what people expect the future to reveal and what institutions are willing to confirm. The wider the gap, the louder the noise that fills it. By 2031, that gap had become an ocean. Panel discussions replaced lectures. Headlines replaced data. The once calm landscape of astronomy became a battlefield of persuasion. Debates raged between empirical purists and symbolic interpreters. One argued that reality ends where reproducibility does. The other claimed that meaning begins where measurement fails. Both were right. Both were exhausted. Within universities, the friction intensified. Ethics committees demanded transparency and funding for Mars follow-up missions, citing public right to observation. He was rested way Kiev is any use for waking flied in the raid. In response, the GSC tightened internal embargoes, insisting that contextual readiness mattered more than immediacy. Contextual readiness, another elegant way to say delay. The rhetoric shifted from what was seen to who gets to narrate seeing. An entire discipline of discourse analytics emerged to track the flow of authority through media ecosystems. Charts replaced telescopes. Word frequency analysis replaced photometry. The data wasn't about the comet anymore. It was about us, how civilization metabolized awe. And yet, amid the noise, something fragile persisted. Curiosity. Even skeptics kept watching, unwilling to let go of the faint ultraviolet heartbeat that refused to die. The Mars data became a mirror, showing not what the universe revealed, but how humanity receives revelation. At a global symposium titled Consensus in an Age of Echo, a philosopher summarized it perfectly. We no longer fight over the existence of truth, we fight over its release schedule. The room laughed, but it was a tired laugh, edged with recognition. Everyone knew the irony. The more connected the species became, the longer it took for understanding to arrive. The journalist who broke the return signal story years earlier wrote a retrospective. The first silence taught us patience. This one teaches us plurality. He wasn't wrong. Truth had stopped being singular. It had become procedural, negotiated between servers, statutes, and sentiments. And through it all, 3I divided by Atlas remained mute, drifting somewhere beyond Saturn's orbit. Its image, frozen in that defiant sunward plume, still appeared in university halls, museum exhibits, and protest banners. A relic, a metaphor, a reminder that even silence can divide opinion if it lasts long enough. By mid-2031, the world had learned to argue in cycles. Each new update from the Global Science Council, GSC, triggered a predictable choreography. First, excitement, then doubt, then dissection, finally, fatigue. The rhythm of belief had become measurable, a sociological waveform with its own frequency. The Media Cognitive Lab, MCL, began tracking it in real time, calling it the institutional pulse. Every controversy left a beat, every silence, a rest. When the next data release arrived, a sanitized Mars continuity report, the pulse spiked again. The document confirmed low-amplitude photometric events, consistent with previous observations, but labeled them instrumental self-reflection phenomena. To the public, it sounded like another euphemism. To scientists, it was déjà vu. The Civic Data Coalition, CDC, responded within hours, publishing a counter-narrative titled The Signal That Outlived Secrecy. They argued that the Mars detections exhibited coherent motion inconsistent with sensor artifacts, pointing to cross-band synchronization between ultraviolet and near-infrared channels. Their charts glowed across social feeds: blue lines versus red lines, consensus versus defiance. Every debate became visual, a duel of graphs masquerading as faith. Television anchors treated the story like a sporting event. Who would win the truth this round? Institutions pleaded for patience. Influencers demanded meaning. For weeks, the tension hummed like a standing wave through the global conversation. Then, something subtle shifted. For the first time in years, both sides started referencing the same data frame, the same timestamp, the same photon count. They disagreed on interpretation, but shared vocabulary. It was fragile, almost imperceptible, but it was alignment. Sociologists noticed it first. They called it consensus convergence, the moment when polarization curves begin to narrow, not by persuasion, but by exhaustion. When everyone is too tired to misrepresent, truth gets a second chance. At a public hearing in Geneva, Dr. Hara Ito of the Mars mission faced a packed auditorium. Cameras flashed, voices layered, questions collided. She waited for the noise to crest before speaking. Her words were calm, deliberate. "We do not claim communication, we claim coherence. And coherence deserves observation, not hysteria." The hall fell silent, not agreement, but attention. In that pause, the institutional pulse slowed. It was the first shared breath between the system and the crowd in years. Journalists described the moment as the return of measured wonder. Hashtags softened. Memes faded into infographics. For a brief span, the internet felt like a seminar again. The GSC followed with a joint statement co-signed by independent researchers and citizen networks. All interpretations remain provisional. All observations remain open. Our disagreement is our method. It wasn't closure. It was a contract, a new equilibrium between transparency and restraint. The discourse didn't end, it learned tempo. Data releases became public rituals, not battlefields. Reporters stopped shouting "cover up" and started asking about calibration. Forums debated error margins instead of motives. Mistrust hadn't vanished, but it had matured. The philosopher who once quipped about truth's release schedule wrote again, this time more gently. After decades of anticipation, perhaps understanding isn't a destination, it's a rhythm. The line went viral, not as outrage, but as solace. People began to treat waiting as participation, not punishment. In classrooms, students simulated the old 3I divided by Atlas datasets, learning how anomalies evolve into principles. Artists used spectral graphs as musical scores. The boundary between skepticism and wonder blurred into something sustainable, critical, awe. And somewhere beyond Saturn, the comet itself remained unmeasured, unspoken, and strangely present. Every debate invoked its name like punctuation. 3I divided by Atlas had become the unit of attention, the heartbeat by which civilization timed its curiosity. By autumn, the Media Cognitive Lab published its final report on global discourse patterns. Its conclusion was simple. Humanity's signal-to-noise ratio has improved. We now pause between certainty and speculation long enough to think. For once, everyone agreed on something. The statement was printed on banners outside research institutes, whispered in university corridors, etched onto digital conference intros. Not triumph, not surrender synchronization. And beneath that new rhythm, the world exhaled. It wasn't peace, exactly, but it was coherent motion, the same kind of order Mars had recorded, now mirrored in language instead of light. In the closing paragraph of her personal log, Dr. Ito summarized the decade with the restraint of a scientist and the weariness of a witness. The signal persists not as data, but as dialogue. We learned that truth doesn't hide, it harmonizes. When her words circulated online, no one argued. They just waited. Because in 2031, waiting had finally become a form of belief. We once measured comets, now we measure ourselves through them. By 2032, the noise had finally thinned into thought. The debates that once roared across continents had settled into classrooms, symposiums, and quiet essays. The story of 3I divided by Atlas, once scandal, then spectacle, had matured into something stranger: curriculum. It was no longer an event. It was a mirror. At the annual Post-Atlas Symposium in Vienna, physicists and philosophers shared the same stage. No one argued. They asked instead, what did we learn about knowing itself? The opening session introduced what scholars now call the post-Atlas framework, a synthesis of plasma dynamics, epistemology, and cognitive theory. It began with a simple premise. Anomalies are not interruptions in order, but expressions of it. Every deviation is a disclosure. Every failure of prediction, a form of communication. Dr. Hara Ito, older now, presented quietly from the front row. Her final slide displayed no numbers, only a sentence. Coherence is not certainty, its attention sustained long enough for truth to arrive. The room fell silent, the way synapses pause before firing. Across the scientific world, this new humility reshaped method. Models became dialogues. Peer review expanded beyond replication to include resonance, whether ideas held rhythm across disciplines. Mathematics itself began borrowing metaphors from music, cadence, modulation, phase drift. The once heretical notion of feedback between light and observer had become the cornerstone of a new epistemic ethos. Students of astronomy now study observer entanglement alongside orbital mechanics. They learned that the universe doesn't merely unfold, it replies. Every act of measurement is a form of participation. Every silence, a mode of response. In that sense, 3i divided by Atlas had never been passive. It had played its role as the instrument through which humanity rediscovered its hearing. The Global Science Council, GSC, formalized this approach into what it called reflective empiricism. 1. Observe without urgency. 2. Publish without dominance. 3. Interpret without ownership. These weren't rules of data, they were ethics of attention. And so the comet, long vanished into the black geometry beyond Jupiter, lived on as a coordinate system for humility. Researchers referred to its resonance angle 5 degrees as both a measurement and a metaphor, the slight imperfection that makes harmony audible. For the first time in decades, science felt less like conquest and more like listening. The awe that once demanded explanation had become the explanation itself. Not everything needed to be decoded. Some truths only needed to be witnessed. The final keynote summarized it best. Perhaps the universe never asked us to solve it. It asked us to stay. We go to the sly. Do not want to stead. Every framework, like every orbit, carries potential futures. The Post-Atlas Working Group outlined 3 scenarios, each less about technology than temperament. Not predictions, but mirrors held up to collective intent. Scenario 1. The convergence model. In this path, science and society continue the rhythm established after Mars. Observation becomes participation. Research becomes conversation. AI-driven instruments learn to filter not only noise but bias, recognizing patterns of interpretation as data themselves. Scholars call it symbiotic empiricism, the idea that the instrument must evolve ethically alongside its operator. Humanity grows slower, gentler, less obsessed with speed. The publish or perish era ends. Knowledge accrues like sediment, not shrapnel. This is the hopeful trajectory, the one where curiosity and humility stay in balance, and the cosmos remains a dialogue partner, not a trophy. Scenario 2. The recursive model. Here, attention folds inward. Data fatigue, cognitive overload, and political entropy push research back into secrecy. Institutions, fearing another Atlas crisis, gate information under the banner of protection. Public fascination curdles into apathy. Awe becomes background noise. The anticipation gap reopens, swallowing trust again. In this loop, the lesson of coherence is forgotten, replaced by competition for narrative control. History contracts, science becomes spectacle, and silence reverts from patience to censorship. It is not a disaster, just amnesia. And amnesia, the philosophers warn, is the most sustainable form of denial. Scenario 3. The transcendence model. The rarest, yet not impossible. Humanity accepts the limitation of comprehension and chooses integration over mastery. Observation shifts from collection to communion. Missions designed less to find and more to feel, to register cosmic structure as extension of cognition. Quantum observers, cognitive neuroscientists, and spiritual phenomenologists collaborate openly, treating consciousness as part of cosmology. The result is a science that neither defends nor preaches, it listens. The era becomes known as the Age of Attunement. The symposium's final report didn't choose among these. It closed with a footnote written collectively by every delegate. Reality will take the path matching our patience. That line became the quiet mantra of a generation raised after Atlas students, engineers, poets alike. In them, awe survived not as an impulse, but as a discipline. They understood what earlier centuries had missed, that progress isn't acceleration, it's coherence maintained through change. The comet may have left the solar system, but its gravitational wake persisted, tugging gently on minds long after telescopes lost sight of it. And as those minds began drafting the next missions not toward discovery, but toward dialogue, humanity entered its strangest equation yet: to learn not what the universe contains, but what kind of listener it requires us to become. By late 2032, the language of discovery had softened. The word signal no longer meant